Good afternoon, Professor.
Good afternoon. All right, we have 2 o'clock. Let me kick this final senior design presentation sequence, which you're presenting today. Let me kick it off. It's a great pleasure to launch this special afternoon, which belongs to the students, because it's not my task to speak a lot, because we have 3 groups which are, of course, excited, because after 2 semester Senior Design 1 and Senior Design 2 build up, and of course a learning curve, the teams have been working on 2 separate projects throughout both semesters, which of course aims to challenge the students to think outside the box, to develop independently designed tools, to make yourself familiar with the multidisciplinary thinking, and of course ultimately to forecast a futuristic design. So the topic I've chosen for this particular class is of special interest, because we are at the brink this year maybe of experiencing 2 companies engaging in the first passenger carrying space tourism flights. Now, these are 2 companies, Virgin Galactic, Blue Origin, very different concepts. What they have in common is that there are 2 systems. One system is pushing the other, whereby the second system eventually is reaching orbit. Both systems have characteristics, of course, of reusability very much. So the goal of the current system has been, the current project for the class has been to, of course, be familiar with the overall notion of space tourism, and the first semester served that purpose. So what we are challenging, what we challenge the student body to engineer and to explore with 3 independent teams has been to explore whether that space tourism service, reaching that altitude with a pleasant cabin environment, would be possible with a single stage, as we like to call it, single stage to suborbital altitude. So that might be a follow-on geometry, which might make sense. And today we are witnessing the results of a project where 3 student teams exclusively focused on the project throughout the entire semester. And having kicked off the origin of the project, I'd like to hand over to the first team in order to launch your presentation afternoon. Maybe as a guideline for how we are administering this, the 3 teams will each present 50 minutes. We try to be very sharp along these lines. 50-minute presentation, and we are changing over. I'd like to ask visitors to collect questions, because the Q&A is administered at the end after all 3 teams have presented. And of course, I'd like as well to remind the 3 teams as well to collect questions, because the Q&A will be particularly enjoyable when you are challenging, querying your equivalent disciplinary or multidisciplinary colleague in the other team throughout the Q&A session. Right, with this, I'd like to hand over to the first team. Let's lean back and enjoy the show. Thank you so much.
All right. Good afternoon, ladies and gentlemen, and welcome to the Albatross Spacelines final presentation for MAE 4351 Senior Design. We'll begin with an introduction to the mission requirements.
Beginning with the history and background of space tourism, we start with the beginning of human spaceflight in the original race to space. 60 years ago, when the Vostok spacecraft carried Yuri Gagarin to an apogee of 320 kilometers. 40 years and 60 days later, Denis Tito would become the first person to pay for a private flight to the ISS on board a Russian Soyuz. A few years later, the Ansari X Prize contest was held to encourage the development of reusable and privately funded designs that could lower the overall cost and risks of space travel. With their Spaceship One design, Mojave Aerospace Ventures won the $10 million prize. This contest jump-started the space tourism industry that led to the founding of companies such as Virgin Galactic and Blue Origin, and is the basis of the research performed for the analysis of wing body spaceship UTA.
The specifics of the project are as follows. The vehicle must take off and land horizontally, undergoing rocket-powered flight to reach the Kármán line. During the vehicle's ascent, the 6 passengers and 2 crew members must not experience more than 3 Gs of acceleration, and during descent, this limit is raised to 5 Gs. The vehicle will be based at Mojave Air and Spaceport and will take off and land on its runway. A diagram of the vehicle's flight path is shown, and the key phases for the mission are takeoff and pull-up, boost, coast, apogee, reentry, glide, and landing. Albatross Spacelines is comprised of a group of 12 engineers, each with a wide range of specialties encompassing 9 separate disciplines. During this project, each member focused on 2 different aspects of the vehicle design process, with 1 member leading each discipline and 1 chief engineer to coordinate the effort. To begin your guide through the conceptual design of the vehicle, let's start with the discipline that oversees the process, synthesis.
Synthesis as a whole is the starting guide to aircraft design. Due to the wide range of vehicles that may be designed, there are many methods the synthesis discipline can choose. However, for high-performing vehicles, hypersonic convergence is the best method due to its total integration approach. This method keeps the vehicle performance goal constant while the aircraft is integrated in size entirely, unlike sizing components such as the wing and propulsion system separately in conventional sizing methodologies. This sizing process results in a set of feasible vehicles that make up what is known as a solution space. The end result of synthesis is to determine a design point from this solution space that can perform the desired mission. After literature collection and review was conducted, the primary sources for the hypersonic convergence method chosen are scramjet propulsion and future spacecraft propulsion systems and integration. Each source contributed valuable insight into the synthesis process. The hypersonic facilities research conducted by NASA and McDonnell Aircraft provided valuable data on previously conceptually designed vehicles that had the mission to fly at Mach 12 for a sustained period of time. With this data and the sizing process understood, the weight and volume budgets were formed. These equations make up the framework for the first multidisciplinary analysis, parametric sizing. Under parametric sizing, the weight and volume budget equations are solved simultaneously by equating the 2 functions. The equations are solved by iterating the planform area until both the weight and volume budget converge and produce a feasible statement. An initial takeoff gross weight result is also produced from this process. Based on the parametric sizing results, a vehicle geometry is then altered such that the geometry of the vehicle matches the converged data. Under the configuration layout process, an existing vehicle geometry will be chosen as the baseline geometry. Once the geometry base has been set, the geometry is modified to accommodate the size vehicle parameters as a result from the parametric sizing process.
The final step of synthesis is the configuration evaluation. This takes the data and geometries from the previous 2 steps and analyzes it through a flight phase analysis for the specific mission. At the beginning of this process, a specific flight path is chosen as well as the specific components of the vehicle weight. The center of gravity and inertias of the vehicle are also calculated here. With these values known, the flight phase analysis can begin. Each flight phase starts with a trajectory and performance calculation and ends with stability control. Shown here are the flight phases corresponding to the ascent of the vehicle from takeoff to the end of coast. If the vehicle can perform the ascent as required, then the descent calculations start. From apogee to landing, the vehicle must meet all requirements set upon it to be deemed feasible. If the vehicle can complete the flight, then a cost and safety analysis is performed. The purpose of this step is to determine if the vehicle is cost-effective and compliant with any FAA regulations that apply to it. If so, then it remains in the solution space as a feasible vehicle that can complete the mission. Shown here is a solution space that came from scaling the sizing parameters tau, fuel mass fraction, and thrust weight ratio. This is the overall solution space for the parametric sizing. As the synthesis process continues, vehicles will be removed from this solution space. This solution space shown contains 1,000 vehicles that were sized for the mission of space tourism. The minimum and maximum sizing values are shown to span from the planform area of 52 meters squared at 10,000 kilogram takeoff gross weight to a planform of 245 meters squared at 45,000 kilograms for a takeoff gross weight. With all these vehicles sized, let's now discuss the geometry discipline's impact on the solution space.
Thank you. The geometry discipline has developed a database of dimensional data for several existing wing-body spaceplanes. The 5 aircraft that have been selected for analysis are the X-Core Lynx, the Boeing X-20, Virgin Galactic Spaceship 2, C-251, and the Ariane AS-2. CAD models of each of the aircraft have been created, and utilizing CAD software in MATLAB, codes are created to A, scale the dimensions of each vehicle for a given platform area, and B, to generate a valid geometric solution space. The creation of the CAD models and database are aided by a literature review. Geometric data for each aircraft is gathered via several official documentation sources, and texts like Shiz, Nikolai, Raymer, Sadri, and Sforzum are helpful in determining the definitions for non-trivial geometry.
The geometry needs to match certain values of the sized vehicles, mainly the platform area and total volume. To do this, the wings are photographically scaled to the correct platform area. The geometry for the solution space shown belongs to the X-core links, and while the vehicle was small and on the lighter side for such a high-performing vehicle, it is not big enough for our mission. So, the fuselage height was increased such that there is sufficient room for the 6 passengers to enjoy their flight and their time in microgravity. The same height increase is applied to every vehicle regardless of the platform or volume. The width of the vehicle is then scaled until the fuselage and wing volumes add to match these total sized volume. This was applied to every vehicle in the solution space, and the vehicles that resulted in insufficient geometry were removed from it. This refinement removed 95 sized vehicles from the preliminary solution space using the linked space geometry. With this now reduced solution space, the analysis of each vehicle can begin to determine if they can complete the mission. Those that successfully completed the mission then have a cost and safety analysis performed and then reviewed. Of the 905 that remained after MDA-2, 235 vehicles were deemed feasible to complete the mission. This is approximately 24% of the preliminary solution space of vehicles. Of those that couldn't complete the mission, the vast majority failed due to either stability and control or performance issues. For stability and control, the main issues were losing aircraft stability or controllability at some point during the mission, while performance had the issue of not reaching apogee due to a lack of fuel or experiencing too many Gs during boost. Insufficient runway length is also a factor that resulted in some vehicles being removed. Compared to the X-core links in Spaceship Two, this solution space does contain values that are comparable to past vehicles designed for space tourism. The Spaceship Two is a second stage vehicle, which results in its required weight and platform area needed being lower than a single stage vehicle. The X-core links was designed for a single passenger that did not experience microgravity as the passengers aboard our vehicle will, so its smaller values are still comparable, but not directly. Lastly, the design point for this solution space has a tau value of 0.1578, fuel mass fraction of 0.575, and a thrust to weight of 1.05. Again, the Spaceship Two and X-core links values are there for comparison.
As mentioned, upon synthesis's application of the MDAs to each aircraft geometry, 4 of the 5 aircraft are deemed unfeasible for the mission. The X-20 reported too few feasible configurations, Spaceship Two's feathering mechanisms add to unnecessary complexity, and both C-251 and AS-2 are too large to effectively complete the mission. Thus, the links geometry is adopted, and after the synthesis sizing process, it's determined that the fuselage length, width, height, and platform area must be scaled up 150, 166, 270, and 302% respectively. The final scaled configuration of wing body Spaceship UTA is highlighted in that lineup on the right. This figure shows a top view of the original Lynx geometry and wing body Spaceship UTA. Unlike the Lynx that is meant to seat 2, our aircraft requires a far larger pressurized cabin to accommodate 2 crew and 6 passengers. The highlighted in purple is the allocation of cabin volumes for both aircraft, and the green shows the topography of passenger locations. The orange indicates fuel allocation, both primary and RCS, and the red indicates the rocket engines. So, more passengers, larger engines, and much more fuel, wing body Spaceship UTA is bigger and far more powerful.
The purpose behind the weights and balance discipline is to produce the lightest aircraft that will engage in safe flight, select an appropriate aircraft airframe and material composition of the vehicle, determine the maximum takeoff gross weight based on the empty fuel, payload, and crew weight, and evaluate the center of gravity throughout each flight phase in order to produce a CG envelope. The primary literature used to develop the refined weights estimation methodology were Roscom's and Raymer's aircraft design text. The primary literature used to develop the center of gravity methodology is the Dre's aircraft design text. Key inputs necessary to begin the refined weights analysis will come from the geometry and propulsion disciplines in the form of vehicle geometry and engine specifications, respectively. Once a material type and structural layout has been decided, the weight estimations of the takeoff gross weight and empty weight can be calculated using empirical aircraft component weight equations that are based on historical data regressions of past vehicles that are similar in mission to that of wing body Spaceship UTA. Afterwards, the center of gravity of the aircraft can be estimated based on the sum of the aircraft component weights in their respective locations from the aircraft nose. To ensure the methodologies created are feasible to the mission requirements of Wing-Body Spaceship UTA, the methods were verified using previous historical aircraft data. To rapidly verify the refined takeoff gross weight and empty weight calculations, a regression plot was generated with 8 vehicles that performed similar missions to that of our vehicle and produce a linear function that relates the two variables together. Using 8 surrogate aircrafts, a trendline of the empty weight based on the takeoff gross weight was constructed to provide a quick estimation of the empty weight. The methodology is based on Roscom's Class 1 weight estimation approach. Shown on the graph on the right, the Bell D-171, Skylon, and the X-20 are vehicles that match closely to the trendline generated from this approach, shown by the low percentage errors when compared to the trendline. The percentage errors of each of the 8 vehicles are presented in a table on the graph. To verify the CG methodology, the weight and geometry values of Spaceship 2 were implemented into the method and compared to its existing center of gravity values. The percentage errors between the methodology results and the existing Spaceship 2 values are presented below. After hypersonic convergence produces an initial takeoff gross weight estimate of wing-body spaceship UTA, refined weight estimations based on Raymer's empirical aircraft component weight ratios were implemented to improve the initial estimate. Assumptions made when implementing the methodology were the inclusion of 2 rocket engines, the airframe composition being made of a multi-spar, multi-rib configuration, and the vehicle being analyzed assumed to have a supersonic cruise vehicle configuration. The refined takeoff gross weight of wing-body spaceship UTA is approximately 14,429 kilograms with an empty weight calculation of 4,808 kilograms. The material composition of the vehicle is all carbon composite, a choice made to reduce the weight of the aircraft. On the right side, the empty weight breakdown is shown visually.
The landing gear must withstand the maximum weight of the vehicle when performing various maneuvers during the taxi, takeoff, and landing phases. Therefore, the design, location, and geometry of the landing gear are needed to further analyze the vehicle. The main literature used to develop the methodology in the IDA on the right is Sedri's landing gear design buildup. For verification of the methodology, the Lynx landing gear design, a retractable tricycle configuration, is analyzed and scaled to the geometry of wing-body spaceship UTA.
The following images present the main center of gravity locations calculated at the empty and takeoff gross weight of the vehicle. The most aft and most forward CG locations were also calculated to develop the center of gravity envelope. As shown below, once fuel has been added to the back of the vehicle, the CG shifts aft, yet maintains within the bounds of the most forward and most aft CG locations. Now we will begin the flight phase analysis, starting with the takeoff phase.
The primary objective of the takeoff is to verify the vehicle can produce enough lift to have the vehicle actually take off the runway. In addition to this, the vehicle must also be able to have the elevons rotate the vehicle properly around the main gear. The primary disciplines responsible for this phase is trajectory performance, propulsion, aerodynamics, and stability and control.
Before the launch, our 2 qualified pilots initiate safety critical pre-flight operations in accordance to Part 37. This includes local notification by notifying air traffic control, hazard area surveillance within the vicinity of the designated spaceport and along the trajectory, collision avoidance on the ground or runway for traffic that may conflict with the day's launch, and meteorological data using FAA's aviation weather services to ensure there is no probability of impact by hazardous debris. Launching with the crew, Part 460 is followed for training, including the conditions for abort scenarios and emergency operations. They must be able to perform safety critical roles under intense pressure. In accordance to 460.9 regarding human spaceflight requirements, notifications of risks that come with space transportation are implied, and the human factors such as the physical stress for acceleration, vibration, and noise are assumed.
The takeoff performance phase is imperative in the design process because it's responsible for sizing the wing of the vehicle. The main objectives of this analysis is to ensure that the vehicle is able to take off within the provided field length. The field length for Mojave Air Spaceport is approximately 3,800 meters. Nikolai's takeoff methodology is used to derive an IDA for the takeoff performance, as can be shown on the right. Next slide. To verify the Nikolai methodology, this analysis is implemented in the Lockheed L1011 TriStar. The inputs for the vehicle are shown in the top right table. With those inputs, imperative takeoff parameters such as takeoff velocity and total takeoff distance can be determined. Those calculations were compared to verification data, and as can be observed, all the percent errors are at or are at or below 1%. This gives way for the methodology to be implemented on the selected vehicle configuration. Next slide. Wingbody Spaceship UTA is a significantly smaller vehicle compared to the L1011 TriStar. Hence, it was expected that the various takeoff parameters can be lower in comparison. As can be observed on the input table, the maximum lift coefficient is much smaller due to the smaller wingspan. Nevertheless, Wingboard Spaceship UTA takes off at a Mach of 0.21, which is well within the typical aircraft takeoff speed. The selected vehicle configuration has a longer takeoff distance of 1,773 meters. Nonetheless, the vehicle is able to take off with plenty of runway to spare. Now for the propulsion team to elaborate on the vehicle propulsion and the takeoff phase.
The methodology development for the propulsion and fuel systems discipline began by conducting a literature search from which 3 books were chosen for the analysis. The steps taken to design a propulsion system are summarized in the diagram shown to the right. 4 different engine configurations are used to verify the methods chosen. Next slide, please. After a thorough literature search, the RL10A4 was chosen for our baseline design due to its lightweight and high performance. 2 of these engines are necessary to fulfill the mission requirements. Next slide. A trade-off between chamber pressure and nozzle expansion is made as shown in the bottom right. Also, the tank pressures are calculated so that there is enough volume to withstand the amount of propellant needed for the mission. The results are shown in comparison with the Space Shuttle main engine in the graph at the top right. Next slide.
The second portion of the propulsion and fuel systems results mainly deals with the performance of the 2 RL10 engines utilized for the mission. The verification method used to obtain the speed and thrust profile of the RL10 engine had a percent error less than 5% and was used to analyze the propulsion system for the final sized vehicle. The thrust required at takeoff was about 56.9 kilonewtons, and seen on the thrust graph, this value is obtained about 34 seconds after firing the engines. Next will be aerodynamics to discuss the aerodynamic analysis for takeoff.
The aerodynamic analysis at takeoff focuses on verifying that the lift generated will overcome the takeoff gross weight of the vehicle. A methodology and IDA diagram were developed as shown with primary literature methods including the US Stability and Control DATCOM and Spencer. Next slide. The subsonic lift and drag wing pitching moment slope methods were verified using the Space Shuttle data and a developed database of delta wings, and most percent error values were less than 15%. For Spaceship UTA, the necessary aerodynamic values were, and it was verified that the wing produces enough lift for takeoff. Next slide. And now on to stability and control.
For the takeoff phase, the most critical part is ensuring the vehicle will be able to rotate the vehicle to the proper angle of attack required for takeoff. Survey was used as a primary methodology in developing the equations of motion, and DACOM was used to obtain the stability derivatives. Next slide. Using Sidray and also Colgren as a reference, the equation of motion for a delta wing configuration were derived and used to evaluate the necessary elevation control authority. The required lift and pitching control authorities are presented, and these variable was used to estimate the size of the elevons required based on the necessary pitching and lift control authorities by the elevon. The elevon control surface area was estimated to be approximately 11 meters squared with an elevon deflection of 15 degrees required to pitch up the vehicle. And now for the next phase.
The objectives of the boost phase involve determining the optimum trajectory that allows Spaceship UTA to achieve 100 kilometers with adequate thrust and stability. Furthermore, the loads experienced during this phase must not exceed 3 Gs. The primary disciplines responsible for achieving these objectives are trajectory and performance, propulsion, aerodynamics, aerothermal, and stability and control.
To develop the trajectory for Spaceship UTA and analyze the performance during flight, the methods selected and verified were Vin's trajectory model and the Nicolai and Raymer performance analysis methods, the steps of which are shown in the IDA to the right. The Space Shuttle and X-15 were selected as verification vehicles because of their low aspect ratio wings and high altitude performance capabilities. Additionally, the X-15 weight was close to the goal weight of the Spaceship UTA. Based on the closeness of the calculated and literature trajectory plots, the methods were considered viable for the Spaceship UTA's analysis. Next slide, please. The top plot to the right shows the ascent trajectory taken by Spaceship UTA, with the corresponding velocity profile depicted underneath it matching up to the trajectory. Inputs were received from the geometry, weights and balance, propulsion, aerodynamics, and the synthesis disciplines. The key boost characteristics can be seen on the slide. After constraint analysis, results dictated that in order to achieve the mission altitude of 100 kilometers, Spaceship UTA must fly on a flight path angle of 60 degrees and requires a thrust of nearly 147 kilonewtons. With these characteristics, the vehicle achieved a propellant mass to total mass ratio of 0.575, which is in the average range for the vehicles of this size. The highest speed achieved was Mach 3.8 at an altitude of approximately 55 kilometers, which is also the point in time where the fuel of the vehicle was fully burned. This occurred 3 minutes and 20 seconds after takeoff. Spaceship UTA is also able to successfully remain within the 3G load limits specified in the mission requirements, where the maximum load was 2.75 Gs. The development of the load over the boost phase is plotted over the speed in the graph to the left. Now to propulsion.
The design challenges that the propulsion discipline will face during the boost phase are stated within D-ideate to the right. For the boost phase, the CG location will change due to the change in orientation of the vehicle. Obtaining the rocket performance is of interest, and during this phase, the engine will cut off and a minimum sized engine will be obtained and analyzed to ensure that thrust requirements throughout the profile are met. Next slide, please. Through the same verified method from the takeoff phase, the thrust graph shows both the throttle engine setting of 50 and full throttle to ensure that the thrust requirement of about 142 kilonewtons are met. A minimum size engine with a mass flow rate of about 42.88 meters cubed per second was obtained and used to size the engine for the mission. The rocket efficiency was measured through a specific impulse value of 371.4 seconds, which was affected by the selected throttle setting. Next will be aerodynamics to discuss the aerodynamic analysis for the boost phase.
The aerodynamic analysis during boost focuses on supplying the drag and wing pitching values for apogee and stability calculations. A methodology and IDA was developed as shown. Next slide. Drag values were calculated after takeoff until the burnout altitude near 55 kilometers and again from the burnout altitude up to apogee. These values were used by trajectory and performance for determining apogee, and wing pitching moment curve slope values were used for stability assessment. And now on to aerothermal.
From literature review, it is learned that one of the limits of the flight envelope is aerodynamic heating. At high Mach numbers, an aircraft heats up due to the conversion of kinetic energy of the air into thermal energy. The increase in thermal energy is represented by the increase in temperature, which occurs due to the heat transfer from the air to the aircraft through convection. Next slide, please. The critical regions of the vehicle are the stagnation points and lower surfaces. Because of this, the aerothermal discipline is in charge of estimating the heating rate at the critical regions of the vehicle. The vehicle used for method verification is the Space Shuttle. Next slide, please.
David, I can't hear you.
Okay. For the boost power descent, US Air Force DACON was used as the main reference and obtained the roll and yaw stability derivatives. Delta wing aircraft found within the references of DACON were used as verification of the DACON equations and methodologies. Errors would range between 5 to 15% depending on the wing configuration and other various required geometric inputs. Aerodynamic parameters such as the wing pitching moment and the coefficient of lift with respect to the angle of attack were obtained from the aerodynamics discipline. Next slide, please. The vehicle was found to be stable for the 3 stability parameters in the subsonic regime. However, as the vehicle crossed into the supersonic regime, the vehicle became less stable, yet still within the static stability requirements. This was expected and can be mitigated through an active control system as seen in numerous modern aircraft and wing body configurations. And now to the next phase.
In unpowered ascent phase or coast, the disciplines of trajectory performance and weight and balance ensure that the vehicle maintains enough momentum to reach apogee and that the loads remain below 3 Gs.
Once the engine shuts off and the vehicle enters into its unpowered coast phase, the weight after the boost phase was recorded. Because the entirety of the fuel was consumed during its burn time, the weight after the boost phase comprises only of the empty weight, RCS fuel, weight of the passengers, and weight of the crew, at a value of approximately 7,095 kilograms. The CG shifts forward approximately to the location of the empty CG location as the back of the vehicle has become lighter.
The coast phase begins once all the propellant has finished expending and the vehicle continues onto an unpowered ascent until apogee. Because the altitude is so high, the density and the dynamic pressure from here onwards is also zero. In the plot to the right, you can see the change in altitude with respect to the Mach number over each flight phase. What's important to note is the decreasing speed over the coast phase, shown in red. Spaceship UTA spends about 70 seconds during the coast phase. Next slide, please.
And now for the phase that everyone enjoys the most, apogee. During the zero gravity phase, Albatross Spacelines aims to maximize the amount of time customers get to spend in the zero-G environment. Additionally, it has determined how much fuel is needed for the reaction control system and the corresponding thrust forces. The disciplines responsible for these calculations is trajectory performance and stability and control.
This is the zero-G region of the flight profile. Spaceship UTA reaches a maximum altitude of 105 kilometers, successfully achieving the mission requirement of getting to suborbital altitude. The vehicle spends a total time of approximately 6 minutes in ascent to get to the apogee point. The vehicle maintains itself in zero gravity and allows passengers to enjoy a free-floating experience in the cabin for about 4 minutes. Next is stability and control.
As the vehicle coasts through apogee and experiences microgravity, typical control analysis methods may not be used. A reaction control system must be implemented to control the vehicle in the non-aerodynamic environment. The X15 is used as a reference to size the reaction control system and develop the equations of motion to obtain the necessary thrust force required and the fuel mass for the exo-atmospheric flight. As can be seen in the table, the errors verified with the X15 are low. Next slide, please. Here, the required thrust forces of the reaction control system for the 3 rotational axes are given, along with the minimum required mass of the system propellant of 200 kilograms. Next slide.
With the passengers strapped back into their seat, we can begin re-entry. In this flight phase, we ensure that wing body spaceship UTA is able to maintain a descent trajectory with an angle of attack high enough for it to reach back to the runway while keeping load factors under 5 Gs and remaining stable. Additionally, it is imperative to develop a thermal protection system that is able to withstand the high temperatures associated with atmospheric reentry. The primary disciplines that work on these objectives is trajectory performance, aerodynamics, aerothermal, and stability and control.
The trajectory and performance discipline will be in charge of determining key values that will be used by aerodynamics, aerothermodynamics, and stability and control disciplines. Griffin methodology was used to calculate the velocity profile and associated altitudes, and Reagan methodology was used to find the deceleration values and the time. Next slide. The re-entry analysis begins at apogee and will fall down into the range of 45 kilometers. This is mainly due to assumptions that were made within the chosen methods. A re-entry skip maneuver is done for the Spaceship UTA mission, which will allow for an increase in speed and will give a max Mach number of 3.57. This occurs at a higher altitude. And this also ensures that the G-force deceleration that is felt will peak at 2.3 Gs and will then have a second peak value. This G-force value is smaller than the allowable max 5G limit that was set by the mission, and the total re-entry time will be 423 seconds or roughly 7 minutes. Now I'll pass it on to the trajectory of the glide phase.
A trajectory and performance glide methodology was developed based on the primary literature sources, including Raymond, Roscom, and Nikolai. Next slide. The space shuttle was used as a surrogate vehicle to verify the accuracy of the velocity time and velocity altitude history methods, and most percent error values were below the 15% threshold, and the method was used to calculate the glide velocity profile history for Spaceship UTA. Next slide. And now for the descent and glide aerodynamic analysis. The aerodynamic analysis during the reentry and the glide provides the aerodynamic coefficients for stability and trajectory calculations. The methodology and IDA shown were developed using primary sources from Kuchiman, Kui, and DATCOM. Next slide. Supersonic methods were tested using space shuttle data, and most percent errors were shown below the acceptable 15% mark. The reentry drag and pitching slopes are shown below. Next slide. During glide, spaceship UTA flies a constant lift-to-drag ratio equilibrium flight from 45 kilometers down to the landing approach, where it is operating at CL max before touchdown. And now on to aerothermal.
The aerothermal discipline is in charge of calculating heat flux values and surface temperatures during the descending phase. The calculations will then be taken into consideration when sizing the thermal protection system. Quinn methodology will be used to calculate the heat flux profiles experienced, and Fink methodology will be used to calculate the surface temperatures. Next slide. The heat flux profile for the lower surface of the spaceship UTA vehicle was calculated assuming a free laminar flow, which will give a max value of about 62 kilowatts per meter squared. But the most important heat flux value that should be checked would be the stagnation heat flux, which was calculated to have a max value of 113 kilowatts per meter squared. The max surface temperature that was measured for the lower surface of spaceship UTA was measured to be 880 Kelvin. With these major aerothermal forces, a thermal protection system will be required for this mission. But due to a carbon-based structure, the thermal protection system can be limited to the most vulnerable parts of the spaceship UTA. This includes the nose, the leading wing edges, and the vertical stabilizers. The material chosen for the TPS was a material called carbon-reinforced silicon carbide. The main reason that this material was chosen was due to the ceramic matrix composite, which gives it a low weight and high thermal conductivity. It is also oxidation resistant, which is a bonus. The total thermal protection system weight that will be applied to spaceship UTA is approximately 1,100 kilograms. Now on to stability and control.
The methodologies used for the reentry and glide phases were similar to that of the boost and coast phases, referencing DACOM. The main critical challenge would be an aft shift of the CG and a high alpha reentry angle of attack. Next slide, please. The vehicle was found to be tending to instability during the high angle of attack for roll. However, using the reaction control system, this is mitigated similar to how the X-15 mitigated its instability during reentry. For the remainder of the glide phase, the vehicle became more stable in both roll, yaw, and pitch. And now to the next phase.
Finally, in the venture to come back home to Mojave, trajectory and performance must ensure that the landing phase that the vehicle approaches at a safe speed and does not stall. Stability control helps complete this objective by sizing the rudder to meet Part 25 landing requirements.
The main objectives of the landing phase is to ensure that spaceship UTA can complete a safe landing at Mojave Air and Spaceport, and the main methodology that was chosen was ROSCOM, which will give different velocity and range values. Next slide. The main velocities that are calculated in the landing phase are the approach and touchdown velocities. The most important factors to ensure that the stall velocity will always be below these values. The stall velocity was calculated to be 33.38 meters per second, and the landing field length was calculated to be 1,146.5 meters. This means that spaceship UTA will be acceptable for landing at Mojave Air and Spaceport. Next slide.
Landing analysis for aerodynamics focuses on determining aerodynamic values on approach through touchdown. Similar methods were used to the takeoff analysis and applied to the landing analysis. Next slide. Lift produced at CL max during landing is sufficient due to the loss of mass from the fuel burned. The calculated aerodynamic values were output to the necessary disciplines. Now on to stability and control.
For the landing phase, the methodology was developed by referencing Cedre as the buildup for the landing equations of motion for wing body spaceship UTA. A subsonic vehicle provided by Cedre was analyzed to verify the validity of the equations of motion and resulted in a 5.75% error. The SR-71 Blackbird was also evaluated to get another reference for code validity in terms of a supersonic aircraft and resulted in a 14.2% error. It was decided that wing body spaceship UTA was to have all moving tail surfaces due to the supersonic flight capabilities and need for the vertical tails to be effective during supersonic flight. With this, spaceship UTA was evaluated to be able to perform a safe crosswind landing with a crab angle of 4 degrees and a rudder deflection of 2 degrees for a crosswind speed of 15 knots.
Now on to the weights and balance discipline to discuss the weight change for the landing phase.
The weight of the vehicle at landing will be similar as the weight after the completion of the boost phase, as all the fuel has been consumed during its burn time. Nevertheless, the RCS fuel used for stability purposes has depleted after the apogee phase, leaving behind only the empty weight and weight of the passengers and crew members. The graphic on the right of the weight changes throughout each flight phase present these results.
With the flight phase analysis complete, we will now do a market and cost analysis of the vehicle.
The market and competition analysis begins with an IDA that was developed using primary literature by the Torrey Group, Futron, and Worcester. An analysis of the market size, and competition were all necessary. From the 8 markets analyzed, commercial human spaceflight proved to be the industry with the highest demand. Further research showed that this sector will be a high revenue generating industry with a lot of potential growth in the future, which was verified by space industry consultancy Northern Sky Research. Next slide. The next step was to calculate the potential market size within the suborbital commercial human space tourism industry using global wealth distribution data obtained from the Credit Suisse Research Institute for the year 2017. Individuals with a net worth greater than 1 million was used for the analysis. This pool of high net worth individuals was further reduced based on research studies and surveys conducted by Futron, in which the parameters seen in the lower left were all applied to the collection of wealth distribution data obtained. Next slide. Futron presented a total number of 6,842 participants in 2017 with a ticket price of $100,000. A number of 7,041 participants was calculated using the methodology developed, which presented a 3% error to the number reported by Futron. Applying this analysis to ticket prices in the range of $50,000 to $250,000, it was concluded that ticket price highly affects the number of participants the company can expect to see, along with the individual's fraction of net worth they are willing to spend on a single large discretionary purchase, as it is seen in the graphs on the right. Next slide. Design is not one size fits all, so there are a number of different configurations that a company can adopt within their design while still being able to achieve the same mission. From this, a number of companies can be seen in the table on the right. Virgin Galactic is the main competitor that Albatross Spacelines will be competing against, in which their traditional configuration of a 2-stage vehicle is utilized, which resulted in lighter vehicle weight. However, Albatross Spaceline's attempt at a single-stage horizontal takeoff and landing rocket-powered spaceflight vehicle proves to be highly competitive against Spaceship Two with the current technology. With a ticket price of $225,000 and a microgravity time of 4 minutes, Wingbody Spaceship UTA also provides ample space within the cabin for the passengers to truly have a one-of-a-kind experience in zero gravity. Now on to Brian to discuss the cost analysis performed.
With a vehicle having been selected, a cost analysis is extremely imperative in determining if the vehicle is financially viable both for the consumer and the company. There are various methods to perform a cost analysis estimation of a vehicle. The 3 most well-known are the analogous, parametric, and bottom-up cost estimation. Each method has its own advantages and disadvantages, but the parametric method is the best option for this analysis due to the ability to predict costs due to operation changes. There are a plethora of parametric cost estimation modeling tools, as can be seen on the bottom right table. Unfortunately, many of them are unavailable due to ITAR restrictions. The transcost method is the best option due to availability and usability. Next slide. The transcost methodology was originated by Dietrich Karler, who published several versions of a cost handbook. This method was developed by examining cost factors of dozens of historical vehicles. As can be seen in the IDA on the right, the methodology is mainly a function of various vehicle weight components and cost factors. It uses the concept of man years to avoid having to account for inflation and the fluctuation of exchange rates. This method allows for the development, manufacturing, and operating costs to be determined. Next slide. The transcost methodology was verified with Virgin Galactic's Spaceship Two flight vehicle, since this is the main competitor of Albatross Spacelines. As can be observed in the table, the methodology results in relatively low percent errors, which deem the process to be reliable. Next slide. With verification of the transcost method, the analysis was applied to the final configuration of Wingbody Spaceship UTA. The development cost of Spaceship UTA is $1.5 billion, and the manufacturing cost is approximately $322 million for one vehicle. This is priced in the Spaceship Two, but was expected due to the higher weight and more engines. However, the operating cost per flight is lower because of the difference in propellant. Using liquid propellant is significantly less expensive compared to solid propellant. Next slide. With the cost calculations having been made, a life cycle analysis can be performed. The first figure on the bottom shows the decrease in manufacturing price for each subsequent vehicle. This is a result of the learning factor. The revenue plot shows that Wingbody Spaceship UTA generates substantial revenue within the first few years, even higher than the Virgin Galactic system. With the ticket price per customer set to $225,000, Albatross Spacelines also generates a higher profit than Virgin Galactic. This analysis shows that a single-stage to suborbit system is financially visible, even more than the current two-stage system. Now I'll pass it to Bree for the final safety analysis.
Thank you. The objective of the safety analysis is to ensure that the vehicle, crew, and passengers, surrounding environment, and company personnel abide by regulations set in place to maintain a controlled area and a controlled flight for the intended mission. This includes applying the correct regulations for both ground and flight safety. As understood from Chapter 701 of Commercial Space Launch Activities, the goal is to safely opening the American people and their private, commercial, scientific, and cultural enterprises should guide federal space investments, policies, and regulations. Next slide, please. The research performed for the analysis tied in with the market analysis for understanding the current safety regulations, including documents stating to the initiation of the space tourism industry. These describe the possible risk factors and positive outcomes that came with the improvements of space transportation. Axel and Larson reports acknowledge the lack of government regulations in regard to experimental vehicles to promote the economic growth and entrepreneurship within the industry. Risk management guidance for launch and re-entry for reusable launch vehicles and the environmental policies and human factors were also taken into consideration. Next slide, please. The calculated and verified ground run from trajectory and performance coincides with that of Mojave runway to be used. For the takeoff flight phase, the launch angle limits were in accordance to Part 417-125, where the nominal launch elevation angle did not exceed 85 degrees. For the power ascent boost part of the launch phase, the gravitational force acting on the vertical plane of the body or amount of G's pulled was less than the limits of at which there is a potential compromise within the body. Next slide, please. Human safety at apogee is what the 2-week training prior to the flight prepares passengers for. This point in the flight phase is where effects of radiation and microgravity come into concern. Solar or galactic cosmic radiation is considered, but for the mere time that is 4.5 minutes that is spent at apogee, this does not imply that the passengers are susceptible to high radiation doses. The microgravity, however, can have musculoskeletal effects, disruption of bodily fluid, gastrointestinal effects, and also cardiovascular effects, which means that, unfortunately, Grandma cannot enjoy a ride on Wingbody Spaceship UTA. Next slide, please. For the safety aspect included in the re-entry and glide phase, Part 450 was followed. It states that the permanent re-entry site must be declared, and per the mission requirements, Mojave Air and Spaceport is licensed and cleared for re-entry and landing. The G's pulled during descent are also lower than the limits proven to have minimal effect on the human body. For landing, the FAA acceptable level of risk approach for a horizontal suborbital vehicle within 80-kilometer radius is used. Next slide, please. With the confirmed parameters through the interdisciplinary analysis, the vehicle has proven its capability in providing a safe and efficient mission for its crew and passengers. The verification licensing used were based on the competitor vehicles that have gained approval and continue to carry out test flights using the FAA-granted experimental permits, which are Blue Origin and Virgin Galactic. Next slide, please.
Overall, the design point chosen by Albatross Spacelines is capable of completing the mission within the given requirements while also being cost-effective and following all FAA regulations. If this vehicle were to enter the space tourism market, it would undoubtedly provide competition to Virgin Galactic's Spaceship 2. With that, that concludes Albatross Spacelines' presentation. Thank you.
Right, everybody, let's just unmute our microphones and let's give a round of applause for our team. Thank you so much. Let us reserve the questions for the end. Please, everybody, take good notes. How convincing, remember, one of the main criteria is how convincing is the pitch. because we have 3 teams. We'd like to compare with who's the most convincing presentation and logic and visualization. Let us now switch to the second team. Thank you so much, Team Albatross. All right, it's all yours.
Can everyone see my slide?
Yes, sir.
Yes.
Sir. All right. Good afternoon, everyone. Here at Helios Aerospace, we strive to make space accessible to everyone. In this analysis, we will be looking at the conceptual design of a blended body space tourism vehicle and making a comparison to Virgin Galactic's 2-stage to orbit system based on our team's results. My name is Jason Seaton, and I am the Chief Engineer of Helios Aerospace. I will now introduce the scope of the project and give some background information before we discuss the costs and business aspects. Here we will answer questions such as how was the process derived, what phases make up the flight path, why are we designing this vehicle, what challenges were faced, and most importantly, what does Spaceship UTA have to offer the paying customer? The purpose of designing a vehicle like Spaceship UTA is to lead towards the first step of opening space to the public, as well as to determine the capability of a single-stage vehicle towards a 2-stage vehicle competitor, Virgin Galactic. Suborbital space tourism in general is a growing industry with several competitors, namely Virgin Galactic and Blue Origin. If Spaceship UTA is more feasible than these 2 suborbital systems, then we may be looking at a revolutionary development to the suborbital space tourism industry in the future beyond that. Let us discuss the flight profile that Spaceship UTA will utilize. There are 7 phases, as can be seen, where each one is visualized in our header with numbering to respective flight phase that represents. Spaceship UTA will accelerate across Mojave Air and Spaceport until a distance has been achieved where the vehicle can rotate to an angle where its lift is greater than its weight. It will then climb to a safe obstacle clearance height and begin power descent until it achieves enough momentum to follow a parabolic flight path to the target altitude of space before re-entering the Earth's atmosphere and following an unpowered glide back to the runway safely. Our team of patrol members is divided into 9 different disciplines, where each of the 9 disciplines has a lead engineer to ensure tasks are being accomplished. To ensure progress is made within the discipline, at least 2 people are in each discipline. A team timeline was constructed to keep the team on track with the conceptual design process and ensure timely progression. We have currently achieved a vehicle configuration that can achieve the mission, but with additional time, we would most likely be able to improve the conceptual design with more refined geometry and design knowledge. We will now discuss the overall design methodology. We derived the process into 3 distinct phases, where an estimation of the vehicle's maximum weight and wing area is analyzed and integrated for a total volume constant to pass down to the geometry team. The geometry team then shapes our vehicle and passes geometrical information to the configuration evaluation team. Based on our results during the phase, it will determine if a process needs to be reiterated or not. I will now hand the presentation over to our cost and market team.
Thank you, Jason. My name is True, and I'm the lead engineer for the cost and market discipline. The uprising era of the space age promises an enormous potential demand for space tourism services that would embark on the business competition between travel companies while introducing new major markets for manufacturing and operating companies to enable true space activities. The topics to be addressed from the cost analysis includes identifying who the current competitors are for suborbital space tourism, how much it will cost to develop, produce, and operate Spaceship UTA in terms of its launch cost and ticket price per flight. Additionally, past to present cost models and literature search for space access vehicles are reviewed to determine the challenges of analyzing the cost for a suborbital vehicle, the design choices that impact the cost, and attempt to maximize its competitiveness, and how Spaceship UTA compares to the current market standards. Next slide, please. The cost and market analysis methodology was derived by defining the key cost parameters, which consist of the cost for the vehicle's development, production, and operation. These estimations are then used to calculate the launch cost and pricing per flight to evaluate the commercial feasibility and profitability of the vehicle. Based on the results of the cost estimations, a sensitivity analysis is performed by modifying the engine options, production units, and launch rate to determine the lowest cost configuration. With the finalized design point, the market analysis is conducted in the context of a space tourism market to compare its launch costs and ticket pricing per flight. Next slide, please. After the verification of the statistical and analytical cost model that indicate a reasonable accuracy for cost estimations at the conceptual design, based on the cost estimating relationships presented in TransCost, the cost analysis of Spaceship UTA was preceded with the assumption that it is characterized as a high-speed aircraft or first-stage vehicle with rocket engine that uses cryogenic liquid propellants. This is because it is an aerospace plane that will take off and land from a conventional runway. Given the key input parameters, the results of the analysis had yielded an approximate launch cost of $8.3 million and a ticket price of $1.1 million. From determining the development and production costs of surrogate vehicles, it was realized that the primary contributors that strongly influence the total cost is the selection of the engines, vehicle system, and propellant, which are measured by their mass, implying that the smaller and lighter the vehicle is, the lower it will cost. Next slide, please. Based on the results of all the other engineering disciplines, it was realized that a single-stage vehicle with an existing rocket engine design was assumed to be technically feasible for reaching suborbital altitudes. According to the sensitivity analysis performed that consisted of the trait studies for 6 different configurations, varying the weights, it was approximated that the ticket price would be about $1.1 million. Since Spaceship UTA is intended to operate as a reusable winged vehicle system with a high launch frequency, it was confirmed that tremendous efforts will emerge from the development costs as opposed to the lower cost of expendable ballistic vehicles. Consequently, the ticket price for the single-stage to suborbit rocket-powered vehicle concept for space tourism is not justified due to its high development cost compared to its competitors, primarily Virgin Galactic Spaceship 2, which is a 2-stage suborbital vehicle system. However, with higher public demand convincing governments to provide some financial aid while potentially allowing higher launch frequencies without cutting the cost, the economic feasibility for this type of vehicle concept can be realized in the near term. This concludes the cost and market portion.
Thank you, Drew. The synthesis discipline oversees the sizing of the aircraft, where the objective is to determine baseline design parameters that are required to build the geometry of Spaceship UTA. In this phase, we will discuss topics such as how much is the takeoff weight estimated to be, what is the wing platform area required for our vehicle, and what are the total volume constraints to integrate the entire vehicle to the geometry team. The overall design methodology for our vehicle, as mentioned in the introduction, was broken down into 3 phases. As seen in the bottom tab, synthesis is the first phase of the design process. Part of the task of this discipline is to develop an overall design methodology, which is accomplished by creating necessary parameters from each discipline by flight phase, such as the time the paying customer will have in zero gravity. Before jumping into the analysis, let's look at how the weight range was determined. The synthesis discipline looked into several suborbital vehicle configurations, such as sounding rockets, second-stage systems, and experimental data obtained from a New Shepard. A linear trend line was approximated between these data points to estimate where Spaceship UTA's weight should be as a function of thrust. It was determined here that Spaceship UTA would be within a 15,000 to 30,000 kilogram range. Let's look at the results now. To verify the sizing analysis of Spaceship UTA, the SR-71 was sized to ensure that the dry weight, total volume, and upper hypersonic convergence parameters were estimating a % error within a reasonable ballpark. Spaceship UTA was then sized after verification and iterated several times with each discipline until a feasible design was achieved at a takeoff weight near 21,000 kilograms. From the approximation discussed earlier, this is about 1,000 kilograms off of the estimation. From the sizing results obtained, a 3D solution space topography was generated to verify the design space obtained for Spaceship UTA. Unfortunately, there are no blended body spacecraft vehicles, nor are there single-stage suborbital systems that Spaceship UTA can directly compare to, so the best fit for verifying this was the vehicle Basinger 2. I will now pass this presentation to the configuration layout team, which handles the second phase of the conceptual design process.
Hello everyone, my name is Enke. I'm the lead for the geometry discipline. During this section of the presentation, we'll discuss the purpose of the geometry discipline, major characteristics of a blended wing body vehicle, the type of experience that passengers can expect from the cabin layout, how the external geometry was determined, and how the internal layout fits within the exterior geometry. Next slide, please. Determining the geometry of the vehicle was divided into 4 stages: sizing the passenger cabin, sizing the wings and the fuselage, determining the location of the internal components, and generation of a 3D CAD model. The size and shape of the cabin would be determined by requirements and reference space access vehicles. The wing would then be shaped to meet the requirements of the aerodynamics discipline and sized to meet the planform area generated from the analysis of the synthesis discipline. The fuselage would then be shaped and sized to contain the passenger cabin, fuel tanks, engine, and landing gear while maintaining the expected cross-sectional shape. The internal layout would then be dependent on the external geometry generated and requirements from propulsion and the weights and balance disciplines. After the exterior and interior dimensions have been determined, a 3D CAD model would then be made using the OpenVSP software for the exterior dimensions and internal layout, and SolidWorks software to determine to model the passenger cabin. The model of the exterior dimensions would then be 3D printed and delivered to synthesis. I'll now hand it over to Kapil to discuss the cabin layout.
Hi, my name is Kapil, and I'm responsible for designing the internal layout of the cabin for passengers. The goal was to design the best possible interior for passengers with maximum comfort in mind. The literature review was done mostly on the interior design of various aircrafts and Roscom's Aircraft Design Volume 3 book. Various cabin layouts designs were considered initially and tried, like the elliptical design on the middle right. However, the limiting factor for different types of shape was the pressurization system for the cabin. So cylindrical shaped final cabin was chosen for the design as seen on the right side. Also, a top view of such design is shown with bold red arrows showing possible places for the placement of spacecraft doors. Next slide. Another important aspect of the internal design is proper seat design and windows arrangements. The windows arrangements dimensions were based on the literature review, and the windows will be made from high temperature quartz glass to withstand heating and cooling at the same time, being crystal clear to see outside. There is also ultra leather by ultra fabrics in the passenger seats that uses the technology of 4-layer performance fabric to add comfort and cushion. The design seat has some mechanical approaches such as low body negative pressure or headresting seat that is efficient as first aid itself to prevent blackouts during the phases. The renderings of the windows arrangement and passenger seat design can be seen on the right along with their exact dimensions on the bottom table. Next slide, please. The most relevant but challenging topic that should be considered is the sightseeing, passengers cabin layout, and some extra space for experiencing weightlessness. The internal cabin layout was finally designed, and the CAD model along with some renderings can be seen on the right side compared to that of the Spaceship 2 design. The bottom table shows the final exact dimensions of the internal layout. Next, Jose will be talking about wing selection.
Thank you, Kapil. In order to get up to speed with the shaping of the wing platform, a historical database of previous high-speed and space-access vehicles was developed. Utilizing historical design case studies, one can obtain the lessons learned and valuable design guidelines that have been acquired over generations. A total of 12 aircraft were selected, which include the SR-71, Concorde, XB-70, Vulcan B-1, Sanger 2, and the X-24B. Geometrical data was obtained and trends were analyzed. From these case studies, it was found that the majority of the high-speed aircraft incorporate a single or double delta wing with sweep angles ranging between 52 and 81 degrees, while aspect ratios range between 1.09 and 2.84. From theory, it was also determined that a subsonic leading edge was desirable for the entire flight profile. This will result in a reduction of wave drag, which is ultimately desirable in order to maintain some excess thrust during the power descent phase. Failure to do so would result in a need for a larger propulsion system, which would increase the weight and so on, thus triggering an undesirable positive snowball effect. Ultimately, Spaceship UTA's wing shape was selected to be a standard delta wing with a leading edge sweep of 74 degrees. This would ensure a subsonic leading edge throughout the flight profile, as well as ensure sufficient subsonic aerodynamic performance for critical phases such as takeoff and landing. Now I'll pass it on to NK to discuss the exterior geometry.
Thank you, Jose. For this project, a blended wing body design was chosen. Blended wing body vehicles differ from traditional aircraft by combining both the fuselage and wing into one body. As a result, the fuselage for the vehicle will also be wider than traditional vehicles. At the current slenderness ratio generated by the synthesis analysis, the cross-sectional shape for a blended wing body lies between a half ellipse and a full ellipse. As such, the cross-sectional shape used for Spaceship UTA was modeled to best reflect the resulting shape. For half ellipses, a height-to-width ratio of 0.05 to 0.5 is used, while elliptical cross-sections use a range from 0.1 to 1. For this vehicle, a range of 0.1 to 0.05 was used to stay within both ranges, can be verified with the ratio used for the Sanger 2 blended wing body, which lies at 0.48. Next slide, please. With the blended wing configuration combining the fuselage and wing and the triangular delta wing used as a wing shape, the length of the vehicle was matched to meet the length of the wing to maintain the planform area. From the planform area obtained from synthesis, a wingspan of 12.07 meters and a vehicle length of 21.05 meters was generated. The curve used for determining the height of the vehicle along the length, determining the height of the fuselage along the length of the vehicle was taken from the existing blended wing body, the Sanger 2. And the maximum fuselage height of 0.269 meters was used to encapsulate the passenger cabin and maintain the curve. The vertical tail for the vehicle was sized and shaped by the stability control discipline to meet their disciplinary requirements. Next slide, please. For the interior layout, the size of the passenger cabin was determined prior to determining the exterior geometry to ensure the fuselage met the size needed to contain the cabin. The location of the cockpit was placed to give the pilots the best field of view required for passenger vehicles. As the nose of the vehicle is larger than traditional vehicles, an external vision system will be necessary for the pilot's view forward. The sizing and shape of the fuel tanks and engine were determined by the propulsion discipline and passed along to the geometry discipline placed within the exterior geometry. The landing gear dimensions and placement were done in collaboration with the weights and balances discipline to determine the best location of the wheels and stress during takeoff and landing. In the event that the interior components do not fit within the exterior geometry of the vehicle, the design process will then be iterated back to the determination of the locations of the components or the exterior geometry determination to ensure the geometry can fit the components while maintaining the sizing values from synthesis. I'll now hand it over to Alejandro for weights.
Thank you, NK. Hello, my name is Alejandro Rodriguez, and I'm the Structure and Weights Team Lead. The Weights, Balance, and Structure Discipline main objectives are to determine and track the weight and center of gravity location through all flight phases, as well as to determine the structural composition of the vehicle. Some of the important questions that the discipline must answer are listed to the left. The first step in the analysis process is to perform a literature review. The primary references found are shown to the right. Next slide, please. An overall discipline IDA was created to detail the methods to be used for the analysis necessary for the discipline. The disciplinary analysis is divided into 4 subdisciplines: weights, landing gear design, balance, and structure. Each IDA details the flow of inputs and outputs between subdisciplines, as well as the flow of inputs and outputs with other disciplines. I'll now hand it over to Ricardo for weights and landing gear analysis.
The objective of the weights discipline is to determine the empty weight and takeoff gross weight of spaceship UTA. On the left-hand side, a preliminary and refined estimation of the takeoff gross weight for the X-15 was verified using Sadri's approach. Spaceship UTA will also utilize Sadri's approach to determine the component and subsystem weights that make up the empty weight and takeoff gross weight. On the right-hand side, a summary of Spaceship UTA weights can be seen where a takeoff gross weight is calculated to be 21,243 kilograms, resulting in a 2.29% error when compared to the synthesis takeoff gross weight. Also tabulated is the weight change experienced during the engine startup and power descent. Next slide, please. The objective of the landing gear is to ensure structural safety upon takeoff and landing. Parameters of interest include the overturn angle to prevent the aircraft from rolling over during ground turn, the tip-back angle to avoid contact between the rear fuselage and the ground, wheelbase, wheel track, and more. Utilizing Roscom's approach, the maximum static load felt by the X-15 nose gear was calculated and used to determine tire dimensions. Roscom's tire sizing, strut sizing, and geometrical layout are further utilized to construct the landing gear of Spaceship UTA. The loads applied to the main and nose gear are designed to carry 89% and 11% of the takeoff gross weight respectively, and the tire and strut dimensions can be seen on the right. Next is Alejandro discussing the center of gravity. Thank you.
Thank you, Ricardo. The determination of the center of gravity location begins with measuring the distance from a reference line to each component's center of gravity. In this case, the nose of the aircraft was chosen as the reference line. Using the calculated weights in these measured distances, the sum of all the moments of the vehicle's components can be determined. The total moment calculated is then divided by the total weight of the vehicle to determine the location of the center of gravity. Next slide, please. Using this method, the center of gravity location of the vehicle was found for all flight phases. At takeoff, the center of gravity is located at 12.74 meters after the nose. This is the equivalent of 41.16% of the mean aerodynamic load. After liftoff, the landing gear is retracted. This shift in the landing gear's center of gravity shifts the overall center of gravity slightly aft. As fuel is consumed through the takeoff and power descent phases, the vehicle becomes lighter in the rear section of the vehicle where the fuel tanks are located. This shifts the center of gravity forwards to about 10.85 meters after the nose. As no further fuel is consumed from the center of gravity remains constant until the landing phase. As the landing gear is set out the center of gravity shifts slightly forward to 10.79 meters aft of the nose, or 26.81% mean aerodynamic chord. This center of gravity range can be observed on the drawing to the right. The range of the location of the center of gravity was also confirmed to satisfy the stability requirements. I'll now hand it over to NK for structures.
Focus on the internal structure of the vehicle was placed on determining a possible structural configuration and the materials feasible for design. For material analysis, the materials were compared to one another through the stress-strain curve, their potential resulting weight, and their compatibility with one another. From the four materials analyzed, the two main materials determined to be feasible were aluminum and carbon composite. While both showed high strength to weight ratio, there's a compatibility issue between the two, as carbon composites have been found to cause corrosion in aluminum when in contact. This can be mitigated by creating linkage between the two materials using steel or titanium. This also reduces the weight advantages gained from using either aluminum or the composite. As such, an internal structure of aluminum was determined to be the best choice for its strength to weight ratio and its use in prior space access vehicles and blended wing body vehicles. For the wing structure, a configuration of closely spaced spars and ribs were determined to be the best configuration due to its high resistance to buckling and its use in prior SAV vehicles. For the fuselage, a configuration with closely spaced frames and pressure dome placed behind the camera was determined to be the best configuration. I'll now hand it over to Jose for aerodynamics.
Thank you, NK. In order to effectively develop an aerodynamic model for Spaceship UTA, the aerodynamic team developed an extensive knowledge and database pertaining to relevant subsonic, transonic, and supersonic aerodynamic methods. The main objective was to develop an individual disciplinary analysis that provides a step-by-step procedure for each flight phase of interest. Important aerodynamic parameters such as lift, drag, and pitching moment are the main deliverables the team will output to other disciplines such as trajectory and performance, stability and control, and propulsion. The table presented on the right pertains to the primary aerodynamic literature collected throughout this course. The literature review consists of two parts, a knowledge base and a database. The knowledge base consists of journals, textbooks, conference papers that address subsonic, transonic, and supersonic aerodynamic design principles. The database consists of technical and experimental data of surrogate vehicles that were used to aid in the development of Spaceship UTA's aerodynamic model. Next slide, please. The master aerodynamic IDA is comprised of 5 distinct flight phases, as shown in the figure on the right: ground roll and takeoff rotation, power descent, re-entry, unpowered glide, and approach and landing. Each flight phase has its own unique challenges and method applications. For example, the takeoff and landing phase consists of subsonic aerodynamics with considerations to ground effect and landing gear contribution. The powered and re-entry phases consist of supersonic, transonic, and subsonic aerodynamics. Thus, handbook methods regarding the subsonic, transonic, and supersonic speed regimes must be obtained and verified in order to accurately model Spaceship UTA's aerodynamic performance throughout the entire flight profile. Next slide, please. For the verification process, the surrogate vehicles selected were the SR-71 and Space Shuttle Orbiter. The SR-71 selected due to its blended body configuration, while the Space Shuttle Orbiter was selected to serve as a basis for the aerodynamic trends during the supersonic and subsonic glide. Several subsonic methods were calculated and compared against test data. Ultimately, the lift methodology developed by Kucherman and Raymer's drag buildup were selected for the subsonic aerodynamic tools. Next slide, please. In a similar fashion, the supersonic methods collected were tested and compared against available test data. For the supersonic regime, DATCOM's lift estimation process, as well as Raymer's drag buildup, led to the least amount of percent error, thus being selected for Spaceship UTA's aerodynamic model. Next slide, please. Spaceship UTA begins with a takeoff ground roll. The vehicle is positioned in a non-lifting configuration, thus the only parameter of interest during the subphase is the parasitic drag. The parasitic drag coefficient with respect to velocity is shown on the right. Once the aircraft reaches its takeoff speed, the pilot begins to pitch up the nose to generate lift. It was determined that enough lift was generated at an approximate angle of attack of 9 degrees. The lift curve slope, drag pull, and aerodynamic efficiency with respect to angle of attack are shown on the right. It was also determined that the minimum required planform area for this phase was approximately 124.49 meters squared. Now we'll pass it on to OC to discuss the power descent phase.
Thank you, Jose. So the power descent is one that is interesting and has its own complexity. Unlike every other phase of the aerodynamic analysis, of course, the primary aerodynamic property that needs to be quantified and reported is the drag in this phase. Now, this is due to the aircraft pitching to about 80 degrees shortly after the ascent commences, thus neglecting the need for lift in its governing equation. Then this, of course, makes it simpler as the focus is now placed on reporting just the parasite drag in components as done on the right of the screen. Now, after the synthesis team, of course, produced sizing for 5 design cases, we're able to select the second case in the project, which accompanies minimal drag during the ascent, which is also overcome by the thrust along the ascent profile. Now I'll pass it back to Jose, who's going to talk about the re-entry.
Once the passengers have enjoyed the view of Earth from space, the vehicle begins its re-entry trajectory. During the re-entry, spaceship UTA encounters high aerodynamic stress. With the rocket powered off, the base is no longer pressurized, and the base drag begins to dominate the parasitic drag buildup. As can be seen by the figures on the right, the lift and zero lift drag coefficients decrease with increasing Mach number. This trend agrees with theory as well as the available test data collected. The aerodynamic coefficients with varying Mach number are presented on the plots on the right. The aerodynamic coefficients calculated during this phase were then passed on to the trajectory and performance team in order to determine the best flight trajectory that meets all the design requirements imposed. I will now pass it on to my colleague Johnny to discuss the unpowered glide and landing phases.
Thank you, Jose. During the unpowered glide phase, L over D would be the most important characteristic. L over D will be used to maximize the range to return to the spaceport. L over D max will shift slightly as altitude changes. To maximize the range, the vehicle should stay between angles of attack of 6 to 8 degrees. If the velocity decreases too much, the vehicle may angle down to gain additional velocity. The neutral point was determined to be 13.3 meters from the nose of the vehicle. Next slide, please. During the landing phase, touchdown velocity was calculated to be 95.5 meters per second. The maximum angle of attack for flare was reported to be 15 degrees. At this angle of attack, the usable CL max with ground effect included was determined to be 0.5587. The actual angle of attack for flare is 6 degrees. This should provide sufficient lift at touchdown for a smooth landing. The minimum required planform during this stage is about 120 meters squared. This will conclude the aerodynamics portion.
Thank you, Johnny. My name is Prabhasha, and I'm the lead engineer in charge of the propulsion and fuel systems. The team consists of 2 members, myself and Kapil, and our goal are to deliver the company with an effective propulsion system to power spaceship UTA. The flight phase analysis with the discipline was split between myself and Kapil as shown in table 1 to the right. I am in charge of the ground roll until takeoff, and Kapil is responsible for the powered ascent. System and sizing designs were also divided among us, and where my job was to design and size the propellant tanks, and Kapil dealt with the nozzle and overall engine sizing. Examples of general questions that are addressed from a propulsion team are: how is the engine and the fuel tank sized? Can the selected engine provide enough thrust for takeoff? What are the incorporated safety measures? To address these questions, let's dive into the design process. Next slide. Proceeding an extensive research, it was identified that the commercially off-the-shelf engine would do the job together with certain modification to the overall propulsion system. To select the best engine, a comprehensive knowledge-based and database literature review was conducted to analyze the engine performance of the commercially available engines. This literature review also included a separate section to oversee the propellants that can be used. Primary sources used in the engine design process was Mattingly, Sutton, and Groening's engine design manuals. First, let's take a look at how the propellant tanks were designed. Next slide. When designing propellant tanks, the primary properties that were looked at is the material, the weight restrictions, fuel and oxidizer volume requirements, and the tank bay area available. Several material properties were analyzed for stainless steel, aluminum, carbon fiber, and titanium alloys. The best strength to weight material was titanium, but careful considerations were used in preparing the shell membrane to have maximum strength to withhold high in-flight pressures and ruptures. The interior of the tanks were equipped with grooved baffles to prevent sloshing and turbulence of the fluids inside. The maximum pressure experienced by the tanks can reach up to 72 psi. Hence, a leak before burst concept will be installed where the ports will exert pressure relief and notify the pilots of a potential hazard. Next slide. The overall assembly of the propulsion and fuel system is shown. The chosen Merlin 1D engines runs on an open gas generator cycle along with the turbopump should provide throttling capabilities necessary to our flight. The final engine configuration properties are listed together with performance characteristics. With these systems installed, let's take a look at how the takeoff analysis was conducted. Next slide. With the previously discussed database and the orbital and the suborbital vehicles that relied on these power systems, engine performances were analyzed. As an initial approach, a list of mid-sized business jets, such as the Learjet 75, the Citation Latitude, and the Praetor 500, with similar wing area and takeoff gross weights were compared to their thrust profiles during takeoff. It was determined that the takeoff thrust range is between 65 to 110 kilonewtons for similar-sized aircraft. Hence, using the performance equations from the previously mentioned authors, we were able to arrive at the preliminary performance results, which were then verified within the plots at the left. The takeoff thrust was determined as 88 kilonewtons from the performance team, and the results show that the engine will provide sufficient thrust for takeoff. Next up, I have my teammate Kapil to accelerate you to space during the powered acid phase.
Thanks, Prabhasa. My major purpose is to analyze and design the Space UTA's propulsion system during the ascent phase after takeoff and ground roll. Primarily, propellant selection analysis was done on different propellants and based on storability, economy, toxicity, total content, energy, RP1 and liquid oxygen combination was selected to be the best for the mission and finalized with Prabhasa. Important parametric analysis was done using NASA CEA codes to get some conversion points for the further calculation as seen on the right. This can be verified from the fact that most of the suborbital vehicles developed or proposed use the RP1 liquid oxygen combination the most from our literature review. Next slide, please. Since the engine sizing was based on an orbital Merlin 1D engine, the sizing had to be done to meet the suborbital mission requirements. For the nozzle design, the method of characteristics was used, which is a numerical procedure of designing the contours of the rocket nozzle at the optimum expansion point. Based on the estimated required max thrust and NASA CEA results, a MATLAB code was written for the method of characteristics. The graph on the top right shows the radius and slope of some points from the center line as obtained from the code. After that, the points were exported to Excel and used in SolidWorks to define the curve, and the nozzle was finally designed. Finally, the table shown consists of important output dimensions for the method of characteristic for further calculation. Next slide. Like the Merlin 1D, this uses pintle injectors for injecting the propellants, and along with the use of turbopumps and valves, can throttle the flow rates, ultimately throttling the thrust of the rocket from 30% to about 90%. Throughout the flight, based on the flight angle and load requirements from the stability and control discipline, the propellant flow rates were throttled ranging from 68 to 98 kgs per second. Also, the fuel mass fraction was calculated to be around 0.467 for ascent phase, and the propellant needed for the ascent phase to be approximately 10,149 kgs. Next slide. Finally, after the combustion analysis, fuel system analysis, and engine sizing, the propulsive output parameters were calculated for the ascent phase. And the ascent phase for my person started from 20 seconds. The thrust profile, specific impulse profile, along with the propellant flow rates were generated. The step points in the curves on the right suggest the throttling phenomenon used as per the loading requirements. Even though the max thrust that the engine can produce is around 352 kilonewtons, only a thrust of 311 kilonewtons was used at the end of the ascent phase. From the simulation, the total burn time was around 143 seconds with specific impulse around 325 seconds, and the main engine cutoff point was around 143, which is very close to that of the X-Core Lynx Mark 1 main engine cutoff point. And next will be Justin to discuss stability and control.
Thank you, Kapil. My name is Justin Ryan, and I am the team lead for the Performance and Trajectory discipline. My discipline teammates are Johnny Nguyen and Osia Kalume. The Performance and Trajectory discipline aims to answer questions such as, what is the takeoff and landing field lengths? How much fuel is required for the mission? And can we reach our target altitude? The literature review to the right is what we've compiled to determine the method for the flight phases. Next slide, please. The entirety of the method is displayed within the following master IDA. This particular discipline requires a wide range of inputs from varying disciplines and reports results to many of these respective disciplines. I would like to hand off to Osia Kalume to discuss takeoff phase for the blended body configuration.
Thank you, Justin. So for our vehicle, we want to ensure that we can take off, of course, in an appropriate time and distance. So with the provided inputs from the propulsion team, we were able to assess the amount of effort that is expended in this phase while meeting safety requirements as set by the FAR 25. So fortunately, the takeoff maneuver, which includes the ground roll, rotation, and transition, happens in about 40.91 seconds while burning a total of 1,763 kilograms of fuel. So an additional advantage, of course, with this vehicle is the fact that the balanced fuel length is, of course, within limits of what is available at the various spaceports in America. So this is actually a pretty good, an excellent performing vehicle. And of course, now I'd love to pass it on to Justin, who's going to talk more about the power descent. Thank you.
Thank you, Ozzy. For the next 3 phases, a 3 degree of freedom simulation for a point mass is used to track the vehicle. For verification of the power descent phase, characteristics of the SR-71, Kuchiman's lift-to-drag barrier equation, and thrust data from the propulsion team was used. The verification showed strong correlation with a trajectory synthesis report using the energy state approximation method described in Ben's text. Applying the method to our blended body configuration showed that we reached our altitude and velocity goal at 56.6 kilometers with a Mach number of 3. Over the course of the trajectory, the maximum dynamic pressure was seen to be at 18 kilopascals, and a slight increase in load is observed early on in the trajectory. Our peak load, this is due to the required lifting forces to reach our target flight path angle. Our peak load is 2.76 Gs just before main engine cutoff, with a final flight path angle of 88.5 degrees. The entire phase required a fuel mass of 9,580 kilograms, which is a fuel fraction of 0.46. Next slide, please. During the coast to apogee, the vehicle is using its burnout velocity and final flight path angle to reach its highest altitude. In order to confirm the method, verification was completed using X-15 and Spaceship One vehicle data and trajectories. The coast to apogee verification results show strong correlation when replicating actual data. The passengers' fun begins as they experiencing microgravity after burnout. The vehicle reaches a final apogee altitude of 105.3 kilometers. At this point, the passengers are seeing some of the best views of Earth. The passengers are now about halfway through with their microgravity experience. Next slide, please. The method and verification for reentry is similar to coast to apogee phase. X-15 and Spaceship One data is used to verify our method. The verification results correlate strongly with each of the vehicle's known inputs and trajectories. For the blended body configuration, its passengers experience a total microgravity time of 3 minutes over the duration of the flight. At 55 kilometers, passengers reach the highest speed during reentry. The Mach number at this point is approximately 2.9. Upon reaching this speed, the vehicle soon after begins decelerating. The maximum load experienced by the passengers is 5 Gs. As the vehicle reaches an altitude of 22 kilometers, the vehicle has traveled approximately 30 kilometers from the airport and must now glide safely back. I'd like to hand off to Johnny Nguyen for glide and landing.
Thank you, Justin. The methodology used to analyze the performance of the vehicle during glide was verified using data from the conceptual space plane. The range must be maximized during this portion of the flight. Given the aerodynamics of the vehicle, it was determined that Spaceship UTA will be able to glide for a maximum of about 14.5 minutes and 123 kilometers once the vehicle re-enters the atmosphere. This range is more than enough to bank and return to the spaceport. The average sink rate was found to be 22 meters per second. The average flight path angle was determined to be about 9 degrees. Next slide, please. For the landing phase, stall velocity was calculated to be about 83 meters per second. The vehicle will need to stay above this velocity. During the approach segment of the vehicle, the vehicle will have a flight path angle of about 5 degrees. It will then flare at 6 degrees to touch down. The vehicle was determined to be able to touch down at 95 meters per second and complete the ground roll within 1,300 meters. This is well within the limits of Spaceport America and Mojave Air and Spaceport. Thank you. Now we will move on to the aerothermal discipline.
Thank you, Johnny. The objective of the aerothermal discipline is to determine the aerodynamic heating and thermal protection that best suits Spaceship UTA. A question of concern is, what is the maximum temperature and heat flux experienced during power descent and reentry? On the right-hand side, the literature review displays texts that originate from Tauber, Bernd, Thornton, and more. Next slide, please. The master IDA is associated with the power descent and reentry flight phase. It begins with a literature review, which is conducted to investigate experimental data of surrogate vehicles and to select an aero heating method for high-speed flight. The aerolist method by Zandbergen was chosen for Spaceship UTA. IDA inputs consist of free stream density, pressure, temperature, and velocity provided by the performance discipline, and the nose radius from the geometry discipline. Aerothermal calculations are then performed, and outputs are distributed to synthesis weights and costs. Next slide, please. The objective of the thermal protection system is to protect the vehicle from aerodynamic heating, similar to Spaceship One and Spaceship Two. Spaceship UTA will utilize carbon fiber reinforced epoxy with a Nomex honeycomb core in low temperature regions. In high temperature regions, such as the nose and wing leading edge, phenolic resin will be used due to its high heat tolerance. Next is Justin Ryan discussing the verification and results for Spaceship UTA.
Thank you, Ricardo. It was determined that the nose stagnation, temperature, and heat flux were of primary interest, as other areas of the aircraft were proportional, if not considerably lower. The method utilizes the convergence of convective and radiative heat rates through the calculation of the Stanton number for the nose of the aircraft. Verification was completed with known heat data for the X-33 and X-34 aircraft and trajectories. The results show strong correlation for supersonic speeds. The results for the blended body configuration show a maximum temperature of 589 Kelvin during the power descent phase and a maximum temperature of 629 Kelvin during reentry. This analysis shows that the temperatures are well within the limits of the thermal protection system. I would like to hand off to Deji for stability and controls.
Thank you, Justin. During development of the Spaceship UTA blended wing body configuration, one discipline is tasked with analyzing vehicle motion throughout the mission profile. The stability and control team breaks down the blended wing body into 3 axes: longitudinal, lateral, and directional. In breaking down into 3 axes, some specific questions regarding vehicle motion and attitude can be asked. For instance, during the takeoff phase, how do you pick the nose off of the ground? Also, if you pick the nose off of the ground, how do you make sure that vehicle motion is maintained, and also you make sure that the vehicle does not continue to pitch up uncontrollably? So the stability and control discipline has an objective to make sure that the blended wing body configuration is controllable and stable throughout the mission profile. The literature review to the right highlights some references that have aided in the analysis carried out in this discipline. Next, we'll discuss more on objectives. Next slide, please. So in a nutshell, this discipline has the main goal of ensuring flight safety from engine on and takeoff to engine off and landing. Static stability is the determining factor of flight safety, and so all flight phases are being analyzed for their static stability. Control surface sizing and control power assessments are also determined using flight phases that place high maneuver demands on the vehicle. Now we perform initial tail sizing analysis. Next slide, please. Spaceship UTA blended wing body configuration features elevons and a rudder as primary control surface effectors. Left and right elevon deflection administers vehicle control in the longitudinal plane, and by differential deflection, vehicle control in the lateral plane is administered. The rudder takes care of directional control. The well-known method of volume coefficients is used to size the elevons and the vertical tail which houses the rudder. For this, a historical database is utilized, and from this pool of information, a surrogate vehicle is chosen and its volume coefficient is used to obtain control surface area. The space shuttle orbiter is chosen as a surrogate vehicle, or you could call it a similar vehicle. Next slide, please. The volume coefficients method is verified by sizing space shuttle control surfaces. With errors as low as 0.5%, results for Spaceship UTA blended wing body configuration vertical tail are highlighted. A planform area of about 8.4 square meters is obtained. Other tail geometric properties are determined by simultaneously solving nonlinear algebraic equations. These are the vertical tail span, the root chord, tip chord, mean aerodynamic chord. Results are also shown to the right. A brief trait study is also performed to show vertical tail geometric properties and their sensitivities to other vehicle parameters. A linear trend exists between wing planform and the vertical tail area. Likewise, an almost linear trend is shown for the vertical tail span. Now I hand it over to True for the horizontal takeoff.
Thank you, Judge. Oh, sorry.
No, you're good. One more slide.
Okay, thank you, Deji. The objective of the analysis for the horizontal takeoff phase was to ensure the longitudinal control surface can provide the required pitch authority to rotate the nose gear to lift off. This is determined by calculating the control surface deflection and control power required for the takeoff rotation maneuver, with the assumption that the vehicle was configured with its maximum weight where the CG is at its most forward location. The results of the analysis had indicated an elevon trailing up deflection of 20 degrees at a pitch rate of 20 degrees per second is utilized to rotate the vehicle for takeoff. Next slide, please. Transitioning into the power descent, the objective for this analysis was to ensure the vehicle is capable of maintaining trimmed flight and has a positive static stability. The method derived to analyze the pitch controller's capability for trimming was done by calculating the control surface deflection and pitch damping for the condition of a steady state straight line flight at all service altitudes between takeoff and upward coast. The results of the analysis exhibited the selected configuration has adequate pitch control to achieve positive stability with an elevon deflection of plus or minus 10 degrees for trimmed flight. Now I'll hand it over to Jason for the upward coast.
Thank you, Drew. The upward coasting phase for this analysis involves determining the implications of inertial coupling and unstable rolling motion at high altitudes on spaceship UTA. A process was derived, and it was determined that if the roll rate is greater than the yaw and roll natural frequencies, then it is theoretically not bound to inertial coupling. It is important to note that aerodynamic control effectors are ineffective at this phase, so the main stability, if determined unstable, reaction control systems would need to be utilized. Upon analyzing spaceship UTA, it is determined that the rolling frequency made the vehicle unstable at these high altitudes, and that for the next phase, a reaction control system would need to be implemented. This was verified by determining the control torque required by the X-15's reaction control system. With the control torque determined for spaceship UTA, these thrusters would need to be placed such that the moment arm is equivalent or greater than the control torque requirement. I will now pass it off to Deji to discuss re-entry and unpowered glide.
Thanks, Jason. Now, for the reentry analysis, a couple of factors were taken into consideration when picking a surrogate vehicle. We needed a supersonic vehicle capable of Mach 3 or in the neighborhood of Mach 3, a similar vehicle configuration or with a similar wing platform, a vehicle with published or declassified data that could be found and used. The F-106B Delta Dart was chosen as a surrogate vehicle for verification for the reentry portion. Since DATCOM is primarily being utilized for the reentry phase, the program example cases were successfully modified and used to verify surrogate vehicle aerodynamic and stability data. Next slide, please. So for the reentry phase, here are some of the calculated derivatives for spaceship UTA blended wing body configuration. We have the pitching moment about the center of gravity, your CM, yawing moment coefficient, rolling moment coefficient, and side force coefficient. Next slide, please. Finally, using the neutral point provided by the aerodynamics team and center of gravity location, the static margin during the reentry phase is calculated. So positive static margin is shown. Next slide, please. That would be all for stability and control.
Thank you, Deji. Now that all disciplines have presented their findings, it's time to see if Spaceship UTA meets the FAA requirements to be certified as a suborbital space tourism vehicle. Licensing and regulatory approval of a reusable launch vehicle is described under Part 14 CFR 431 in the US. The primary objective of meeting these requirements is to ensure all passengers, including the crew, are safe during the mission. The Federal Aviation Administration oversees any atmospheric or space launch activities in the US and have documented certain requirements that need to be met in order to obtain a license for the operation of the vehicle. Space vehicle licenses come in various types and formats which are bound by specific rules and regulations. They can either be an operator's permit, an experimental permit, or a license. The process duration of these licenses varies from 18 months for a permit up to 5 years for a license. The requirements for our mission can be broken down into two segments: the horizontal takeoff and landing regime and the human spaceflight requirements. Let's have a look on the boundaries associated with the horizontal takeoff and horizontal landing regime. Next slide. A vehicle taking off and landing on a conventional runway are subjected to takeoff and landing rules governed by the sections 23 and 25 of the Federal Aviation Regulations Code. The appropriate regulations and limitations to completing this sector was determined using Roscom and Tornbeek's textbook on airplane synthesis. As shown under governing limitations, each flight phase has its designated takeoff, stall, approach, and landing speeds defined. According to these standards, the vehicle should have a takeoff speed of 1.1 times the stall velocity and with a climb gradient of more than 300 feet per minute. The takeoff gross weight should be greater than 6,000 pounds for subsonic airplanes with cruise sailing. Next slide. When looking into human spaceflight requirements, this zone is governed by Part 460 of the FAR regulations. This section defines the rules that need to be engaged during space tourism transportation. Some of the individual standardizations required is to check if the crew is fully qualified, the passengers are sufficiently trained, and also human factors are included in the safety and hazard analysis. Environmental and life support systems in place to enhance passenger and safety comfort. In the event of a catastrophic failure, Part 460.17 defines that an emergency response plan and a mishap investigation plan needs to be established. With our team contributing to satisfy all these requirements, let's take a look at the final characteristics. Next slide. The checklist on the left shows what parameters were required and if these are met. The table compares the results with that of the FAR 23, 25, and human spaceflight requirements. It can be confirmed that all rules and regulations are met on the design vehicle to obtain an experimental permit to conduct flight tests. Thank you. Jason is up next with concluding remarks.
Thank you, Prabhasha. To conclude this presentation, it's important to highlight on the lessons learned from this project. There are very few suborbital vehicles in general, which made verification difficult to quantify for some disciplines. In our case, there are no suborbital blended body vehicles to even reference, which makes this analysis of contribution to the aerospace world. It is estimated that in the future, suborbital space tourism will have a decrease in revenue cost, which could open the door to an aircraft such as Spaceship UTA. For a different direct comparison with Virgin Galactic, it is seen that our single-stage system has a lower takeoff weight than the combined system of Virgin Galactic. This concludes our presentation. Thank you.
Right, wonderful. Let's follow the procedure to unmute our microphones and we will provide. Thank you so much for our guests. What we are doing is we are holding our questions. We are noting them down for our 3 teams, and we are reserving this for the final Q&A at the end of the next team, which is coming up right now. Remember, one of the primary criteria is which team is the most convincing team, the most appealing for the passenger, because again, the passenger wants to have an experience. It likes to see the cabin layout. It likes to find out how long is that coasting maybe happening. And of course, there's the technical quality as well, which is playing, of course, a significant role. Okay. Jens, you are next. Thank you.
Okay, let me just share my screen real quick. Okay, checking if everyone can see my screen.
Number one, you guys look good, and number 2, we can see your screen.
Okay, thank you. Good afternoon, everyone. My name is Sushil Kinekar, and I'm the Chief Engineer of the Beach Sub-Orbitals company, a subset of the Aerospace Vehicle Design 2 class. Today, my team will be presenting our senior design capstone project results. Before we get into the details of the project, some context is necessary. We've already established that flight has always been considered as a prestigious concept ever since the first flight. In the past century, mankind has taken to the skies and has started venturing out into space. First man in space, first man on the moon, and a government program designed around making space accessible to the public are feats which were impossible a century ago. Private companies such as Blue Origin, SpaceX, and Virgin Galactic have also started investing in the space industry, since the government-run agencies lack the coordination for a profit-making program. But today's technology is still limited as space launch systems are vulnerable to external factors and are not that convenient. A single-stage space vehicle which can employ horizontal takeoff landing methods and which can operate in and out of commercial airports is now a feat that the future holds and is the key to making space more accessible. The team was formed by 13 engineers and they were split into individual disciplines. These consisted of synthesis, aerodynamics, geometry and landing gear, stability and control, propulsion and fuel system, weights, volumes and structures, cost, safety and certification, aerothermal and TPS, and trajectory and performance. Simulation was also added after an interest in visualizing the overall trajectory was expressed. A timeline was created to track the company's overall progress to develop our new aircraft aspiration. The mission profile was investigated by the entire company to highlight important concepts from the different phases in the mission profile. A questionnaire was created to categorize the business case questions and the engineering case questions, which were used by the engineers to create their interdisciplinary analysis. The mission requirements stated that that aspiration will be a new aircraft for space tourism, specifically an all-body rocket-powered single-stage to suborbit vehicle, capable of going beyond the Kármán line with 6 passengers. Aspiration will employ horizontal takeoff landing methods and will be designed to operate in and out of airports such as the Mojave Air and Spaceport. The space tourism industry is expecting an economic boom over the next few decades. Currently, companies based in America dominate the space tourism market, and main competitors are Virgin Galactic, Blue Origin, and SpaceX. With the available spaceports and launch sites, Aspiration will be able to serve across the world with the future possibility of point-to-point transfer. Target markets for this sector include not only microgravity research, but also other important niches like astronaut training and experimental technology tests. Now we'll move on to parametric sizing. Parametric sizing will be the first step in determining basic aircraft characteristics. It'll give a first-order approximation of our vehicle.
Here's the literature review that was conducted by the synthesis discipline. Next slide. From the results, next slide. Yep, there we go. From the results of our literature review, hypersonic convergence was chosen to size aspiration. This allowed for an integrated vehicle geometry to be created. The process resolves around solving a weight and volume budget equation until the takeoff gross weight and planform area of the vehicle converge. This allows for a wide variety of configurations to be quickly tested by changing a few input parameters. Next slide, please. Here, the parametric sizing MDA can be seen, which implements hypersonic convergence. The end result of this MDA will be a solution space which visualizes all possible design points and viable design points with the lowest possible takeoff gross weight selected. The variety of design points are created by iterating the slenderness of the vehicle, the fuel fraction of the vehicle, and the number of passengers that will be carried by the vehicle. Next slide.
SK, you're muted.
Sorry, thank you. Using this methodology listed earlier in the slide, solution space was created and a small sector of this solution space, 9.61% to be exact, which is situated below the red constraint plane, contained all of the possible configurations for aspiration. It contained varying takeoff gross weight, planform, and weight ratio numbers, along with tau and passengers. This methodology was verified by using the Spaceship 2 data and X-24B data. The design point was calculated to have around 22,881 kilograms as takeoff gross weight with 74 meters per planform and 0.4 fuel fraction. Now moving on to configuration layout. This phase will explore different aircraft configurations with the design point obtained from parametric sizing. With the design point from parametric sizing, an MDA was created to highlight the configuration layout methodology. Rapid CAD prototyping was heavily used for visualizing different configurations, and methodologies generated by the individual disciplines were utilized to validate the configuration according to the mission requirements.
Hello, ladies and gentlemen. I have the privilege of explaining how the geometric features of the aspiration came to be. To begin, the geometry team considered some critical design questions. Some of the foremost questions on our minds as the engineers of this experience were those of the cabin configuration design. Is it volumetrically efficient? Are our passengers comfortable? And how much space is there? To see how these questions might be answered, we compiled a detailed literature review supported by research and well-known aerospace authors. Next slide. From this literature search, a detailed design plan was made, and it is illustrated here. Next slide. Once we made our plan, we had to check that it worked. We used our process to make sure the numbers came out correct for the HL-10, a simple and early lifting buddy aircraft design. It was a success, and the differences between our calculations and the actual known values were within an acceptable margin of error. With our methodology validated and the preliminary sizing finished, the team could move on to the configuration layout phase. Our team iterated through a myriad of different design points, working out mistakes all along the way to refine the design of the aspiration. Next slide. The first design point was developed as a rough outline of the early solution space model obtained by synthesis. The image shown here is a basic concept model obtained from convergence code visualizers. It was dubbed the ice cream cone for how aesthetically unappealing it is, and it barely followed an elliptical shape with an eccentricity of 0.934. Our team had to go back to the drawing board. Next slide. The second design point was characterized by a slimmer profile, but overall increased volume and planform area. However, guidance from our CEO suggested that the shape of the aircraft would be more aerodynamically efficient at lower speeds if it were slightly more angular. Next slide. And thus, the third design point was born, which flattened the shape to use a more trapezoidal cross-section as the base. However, it still had an oversized volume and planform area. While outlining the internal space of the aircraft, the geometry team noticed that the fuel and oxidizer volumes were too small to make any sense. An error was found in the solution space code, which led to a complete overhaul of the design. Next slide. The fourth design point is the penultimate iteration of aspiration, sporting a much smaller volume and area. However, the change in convergence code deemed requisite a change in engine type, since the initial design engines had a lackluster thrust profile. After this long and arduous journey, the reached Sub-Orbitals obtained its final design point. Ladies and gentlemen, it is my pleasure to introduce to you the RSO aspiration. Next slide. It has a swept-back delta planform design that helps with the flight at higher speeds, and two vertical fins on top to provide stability control. This sleek and stylish profile is sure to carry you to new heights as you reach for the stars. 18 windows allow you to take in the beauty of Earth as you revel in your newfound title of astronaut. A traditional door allows for easy access into and out of the cabin space. Next slide. Detailed specifications are shown here, sporting a 74-degree wing sweep, a tau of 0.162, and a planform area of 74 square meters. The aspiration is a beauty to behold. It is 15.7 meters long and 7.3 meters of maximum width. Inspirations for our design were the Lockheed Martin X-33 and, in part, the X-24B. Next slide. A 3D printed prototype of the model has been created as well and is exhibited here. And finally, I have the pleasure of introducing you to the end user experience and a world first showing of the cabin interior. Miguel Navarro will be your guide in the next slide.
Welcome to the best experience you will ever have. Here in Reach Sub-Orbitals, the geometry team worked together to build this cabin, calculating every minute detail to enhance your experience. Walking up and opening the door will start your journey into becoming an astronaut. Past the door, you can see that there's empty space. This empty space, due to higher bolometric efficiency, will allow you to experience the full weightlessness once we allow you to unbutton your seatbelts for a free roam experience. Next slide. Past this, you can see 6 seats that are shaped in a B format. This B format has been set up strategically to enhance the experience, the comfort level, and to maximize safety. Each seat will have windows on the roof and to the side to give you multiple viewpoints to see the beautiful blue earth. We designed the seats to incorporate the highest levels of materials that will make it feel like you're sitting in a luxury car driving on the streets of Dubai. The seat is held up on a titanium composite stand that will keep the seat from experiencing any unnecessary motion. Underneath, a light was added to round the floor for an additional light source for when you're moving about. In front of the cabin, the 2 pilots can be seen. These pilots are highly trained and equipped with state-of-the-art equipment to get you to space and back home. Here in Reach Sub-Orbitals, we don't aspire to be better than our competition. We know we have reached that goal. Next slide. We have decided to render the astronaut's point of view to showcase the interior of the cabin. We wait once we get to the door to open up so you can see your dreams to come true. Taking a step inside, you can see the designated space and black carpet that you will be floating above. Countless numbers of windows can be seen for your viewing experience. Now let's find you a seat. We will take off shortly. Next slide. We have decided to section off the spacecraft into 3 sections. The aft, measuring 4.51 meters, will house the engine, landing gear, and both fuel tanks. The center will house the passenger, which has been shown to you. The overall length of the cabin is 6.17 meters. Past the cabin, the remaining 4.903 meters will house the electronic system, the nose landing gear, and RCS thrusters. Next slide, please.
During the parametric sizing and configuration layout phases, 2 different propellant combinations were examined. The first being liquid hydrogen, liquid oxygen, the second being RP1 and liquid oxygen. Liquid hydrogen and liquid oxygen having a lower average density resulted in a higher fuel volume and a larger vehicle. The RP1 liquid oxygen design that was eventually chosen had a lower fuel volume of just over 9 cubic meters. Next slide, please.
The propulsion and fuel system discipline for the configuration layout phase will now be introduced. The propulsion team complete IDA shown to the right, where text from Sun and Humble were primarily used to influence our methodology. For the configuration layout phase, critical design questions to be answered were what type of engine is best suited, what propellant can be considered, and how does it impact the vehicle design, and what performance parameters for single-stage vehicles should be emphasized. Next slide. Initially, the propulsion team began with an off-the-shelf database consisting of rocket engines from various manufacturers. Within this database, liquid engines were prioritized as they achieved higher performance compared to their hybrid and solid counterparts. Most of these liquid engines contain the high-performing bipropellant combination of liquid hydrogen and liquid oxygen. Although this propellant combination results in high tank mass and low mass fraction due to its extremely low density, it will make up for it with its high performance. Because of this, Aerojet Rocketdyne's RL-10A5 and RS-25 engines were 2 first candidates to power vehicle aspiration. Though it was quickly realized that a middle ground could not be found with our design points, either numerous RL-10 engines could not meet the performance requirements, or the RS-25 was proven to be too powerful for our needs, regardless of its throttle setting. The third candidate was SpaceX Merlin 1D engine, using the Falcon 9, comprised of kerosene and liquid oxygen propellant combination. Kerosene provides a lower performance than liquid hydrogen. It is significantly denser, requiring smaller and lighter tanks, while also having a relatively low cost in comparison. The Merlin engine also has an advantage in having a wide throttle range, being able to throttle down to 40% by using a stored amount of propellant to adjust turbine power, decreasing the flow of propellant, thus decreasing thrust. This was found to be useful during the takeoff and climb to satisfy the thrust requirements and load factor limitations. With low toxicity and single-stage suitability, the Merlin 1D engine was Reach Sub-Orbitals' engine of choice. Next slide.
The tail of a spacecraft is incredibly important for its stability. Therefore, the size and shape of the tail was greatly considered. To determine the area of the tail, we created a big list of similar spacecrafts and identified any strong trends. To determine the geometry of the tail, we wanted to take a closer look at the X-24C and the Dream Chaser, since both vehicles are rocket-powered lifting bodies with similar mission requirements. We knew that the tail had to take a similar form. In addition, the control effectors or flaps seen on the tail were made to be about 1/3 of the area as seen through historical data. The heavy reliance on historical data is acceptable for the initial sizing since most of the research is already done for us. In the end, if our analysis proved that the tail was too big or too small, we can resize it. Next slide.
Now moving on to configuration evaluation, where the design point will be extensively analyzed. This slide highlights the configuration evaluation MDA, where the configurations from the previous MDA are extensively analyzed to obtain in-depth analysis results for the design point. This process will be carried out with the disciplines working closely together and further refining the first-order studies from the previous phases.
The weights team is responsible for anything involving weights, such as gross takeoff weight, operating empty weight, CG location, and how it moves, body inertias, structural weight, etc. The image on the right is the weights IDA, or design plan to calculate all of these important parameters. Next slide. The center of gravity is an important parameter for most, if not all, of the team. It determines the placement of the landing gear and reaction control thrusters, the stability of the vehicle, and used for many other calculations by the team. The CG, as well as the body inertias, can be calculated by reducing all of the major components, such as the landing gear, fuel tanks, passengers, etc., to point masses and measuring from a reference point. A careful eye must be kept on the CG as it moves during the flight, since the stability of the vehicle is heavily dependent upon it. Next slide.
Hi, so a tricycle type landing gear system was used for aspiration, and having the system, the load needs to be appropriately divided amongst the main gear and nose gear. To be able to have ground stability, the nose gear cannot carry less than 5% of the load or more than 20% of the load. The main gear is seen to carry about 80 to 95% of the total load. In my analysis, the nose gears will handle 10% of the load, as the main gear takes the rest of the 90%. And knowing these appropriate loads, the main gear and the nose gear could size the tires accordingly. The location of the main gear was constrained by the CG, and the angle of attack was seen to be 16 degrees. And having this constraint, the height of the landing gear needs to be greater than 1.3 meters to have a clearance for the back end of the vehicle as it takes off. The track length can now be sized to be 4.25 meters in length, and the placement of the nose gear is placed 8.04 meters from the CG. And knowing the track length, it was seen that the overturn angle of aspiration was 36 degrees, which limits the vehicle from tipping over. Now on to the next slide.
Now we'll transition over to the takeoff phase.
During the takeoff phase, the main question that the weights, volume, and structures discipline aims to answer is what is the takeoff gross weight of the vehicle? Two methods were examined to determine the takeoff gross weight. The first was using a log-log relationship between the operating empty weight and takeoff gross weight of the vehicle, or using a buildup of the operating empty weight to estimate that takeoff gross weight. The buildup of the operating empty weight was selected to estimate takeoff gross weight, and this method was verified using the X-24B. Next slide, please. The first step of building up the operating empty weight was to determine the structural weight. This was done using empirical relationships for lifting body vehicles. The structural weight was found to be 4,177 kilograms, with 92% of this weight being made up by the fuselage of the vehicle. The material of the structure is aluminum. Next slide, please. The remaining properties, or the remaining components of the vehicle, were also calculated using empirical relationships found for lifting body vehicles. Next slide, please. These weights were then summed to get an operating empty weight of just over 13,000 kilograms, which represents a growth of 448 kilograms over the parametric sizing operating empty weight, which is within the 5% target that was set for the weights discipline. Next slide, please. To finish off the estimate of takeoff gross weight, the payload weight and the propellant weights were also calculated with a final takeoff gross weight value of 23,124 kilograms calculated, which represents an increase of 243 kilograms over parametric sizing, which was also within the 5% difference set as a target value. Next slide, please.
And here we have the IDA, which is the technical map that the propulsion team took to find key parameters for the propulsion discipline. The Merlin 1D is an engine that has been used, and its performance can be found through literature, but has to be evaluated for this spacecraft. This is done by finding the thermochemistry values such as the pressure and temperature the fuel reacts in at the required altitude. This is passed on to nozzle flow. Through nozzle flow equations, we can find parameters such as thrust and ISP. With thrust, the mass flow rates, or how much fuel is being used, is calculated. The performance team, looking at historical data for the Merlin, told us to acquire the data at the lowest throttle setting. Next slide. Through the process outlined before, these thermochemistry numbers on the top right are used, and we can see the thrust acquired at the lowest thrust setting is 257.7 kilonewtons. The ISP is calculated to be 304.8, and the mass flow rate is 86.176 kilograms per second. Next slide.
During takeoff, the aerodynamics of the aspiration are critical. Major questions must be answered. Will there be a sufficient lift to take off? Will this lift generate too much drag? And can we keep going after the takeoff? To answer these questions, we must take in the flight conditions for takeoff and the geometry of the aspiration. This information can be used to output a parametrically sized VSP model, which will help us produce the aerodynamic coefficients and forces and moments due to the flow. Next slide. The process of creating a parametric model involves setting custom parameters based on design requirements of the aspiration. This model can be run through the OpenVSP aerodynamic tools. A parametrically sized model makes for quick and efficient changes, and so aerodynamic analysis of every iteration of the aspiration is easy. Next slide. The data output from the OpenVSP parametric model must be validated before it can be used. The values are plotted against historical methods for analytical aerodynamic values. The VSP model will be able to output the primary forces, moments, as well as lift and drag coefficients. Shown here is the validation of the lift and drag terms at a range of Mach values and shows accuracy throughout the phase. Next slide. Now that the process has been validated, it may be used to display the takeoff analysis. The takeoff phase is critical as it is the lowest speed with the highest weight, requiring the most lift to continue. This shows the aspiration's possible solution regions for takeoff where excess lift is successful and the intersection is optimal. We are confident that the aspiration is able to take off based on this analysis. And next slide, please.
Hi, in the takeoff analysis for trajectory and performance, some crucial questions must be answered, like the transition to climb altitude, the takeoff field length, and the velocity at liftoff. Therefore, on to the next slide. The takeoff analysis for aspiration started by knowing that the Merlin 1D engine can be operational at 40% thrust. Therefore, the speed of the vehicle can be calculated along the runway. The speed of the vehicle along the runway accounted for the drag force along with the friction force of the landing gear. Aspiration was seen to reach a Mach number of 0.316 for the takeoff speed. The total ground distance was calculated to be 884 meters in length. The passengers don't feel any G's greater than 0.64 at the end of the runway, and the angle of attack was seen to be 16 degrees in correspondence with the lift velocity of aspiration. Now, the transition to climb maneuver was seen to take 5 seconds to start the climb at an altitude of 1 kilometer. Now passing it on to stability.
For any airplane or spacecraft to be stable, the vehicle must have the tendency to return to its initial orientation after some disturbance or gust of wind. Essentially, the vehicle must produce a restoring moment that rotates it back to equilibrium. With data obtained from the aerodynamics team, we were able to generate these plots that would help us determine if the vehicle is inherently stable or unstable. For takeoff, 3 flight conditions were selected to be analyzed. The top left graph is the pitching moment as a function of angle of attack and must have a negative slope, which it does. The middle left graph is the yawing moment as a function of side slip angle and must have a positive slope, which it does. And lastly, the bottom left graph is the rolling moment as a function of side slip angle and must have a negative slope, which it does, meaning that aspiration is stable for takeoff. Next slide.
According to Federal Aviation Regulations, Section 25 requirements, the takeoff phase needs to have takeoff and climb velocities that are small multiples of the stall velocity, and there must be clearance above 10.688 meters. These requirements are satisfied by the aspiration, and with this verified, we can move on to the next phase.
To aid in the configuration evaluation stage of conceptual design, our team developed and utilized our simulation discipline. Before you on the right is our individual disciplinary analysis based on the work of David Allerton, author of Principles of Flight Simulation. And on the left is a small sampling of the software that our team developed to simulate our spacecraft, which will be visualized using the open source software Flight Gear. Throughout the remainder of the presentation, I will have the pleasure of joining you as we dive into the exciting world of suborbital space tourism with Reach Sub-Orbitals. Ladies and gentlemen, we begin at Mojave Air and Spaceport, located in Mojave, California. If the guests would please take their seats and strap in, we are about to embark on the journey of a lifetime. In just a few short minutes, you will be floating amongst the stars. We promise our destination is out of this world.
Now transitioning over to the climb phase.
Having selected the most appropriate engine during configuration layout, the power descent configuration evaluation focuses on answering critical questions like what will be the thrust and specific impulse profiles as a function of altitude, how many engines will be required, and if a throttle mechanism will be required for the power descent. Next slide. To answer these questions, the thrust and specific impulse profiles at 100% capability were determined based on the propellant thermochemical properties and the physical characteristics of the nozzle. Working closely with trajectory and performance, the ascent of a single engine at maximum power was tested, and it was identified that even though a single engine was capable of satisfying the altitude mission requirement, it did not satisfy the maximum acceleration constraint, meaning that it will be required to throttle the engine. Results from analyzing the thrust to total vehicle weight ratio and the ascent performance indicated that throttling the mass flow rate intake below 65% will result in the vehicle not being able to accelerate and ascend, while the throttling above 75% would exceed the load limit. Consequently, the engine throttling was selected to 70%, resulting in the mass and thrust properties shown in the table to the right. Next slide.
During climb, the aerodynamics of the aspiration are less critical than takeoff, but there are still major questions to be answered. Can the aspiration generate enough lift to rotate through the pull-up maneuver, and can it have sufficiently low drag for the near vertical flight path? The inputs necessary are the flight conditions and limitations for the drag value based on the thrust available, as well as the model from the takeoff phase. Then the outputs are the aerodynamic coefficients as well as the geometric adjustments where necessary. Next slide, please. Using the parametric model from takeoff, the coefficients can be found for the climb conditions and validated using historical methods. The high-speed flight conditions show drag errors as more refined OpenVSP methods are used. Next slide, please. After validation, the climb aerodynamics can be visualized as drag and thrust over a range of Mach values and angles of attack. This shows the aspiration's ability to accelerate upwards without excessive drag during the climb phase. Next slide.
Knowing the platform area, the initial weight for climb, and the propulsion and aerodynamic profiles during descent, it was then possible to develop trajectory analysis for aspiration. The focus of this analysis was to answer the critical questions of what the main engine cutoff altitude must be in order to reach space, and if the maximum load factor constraint is satisfied for customer commodity by generating the trajectory map, the load factor behavior, and other performance characteristics. Next slide. Using the energy state approximation method, with an initial Mach number of 0.35 at 1 kilometer as identified from the trajectory and performance takeoff analysis, and accounting for the maximum load factor constraint among others, the main engine cutoff altitude was determined to be at 46 kilometers at Mach 3.52. From the energy state approximation method, it was identified that to reach space, an energy height of at least 100 kilometers must be obtained. Since such energy height is reached, as shown with the rate energy height contour in the figure to the right, it was concluded that the current power descent trajectory will enable aspiration to reach space with a maximum load factor of 2.8, thus satisfying all the requirements. Next slide.
The same stability analysis from takeoff will be applied to the climb phase. In this phase, we identified 9 important flight conditions. On the top left graph, all the slopes are negative. In the middle left graph, all the slopes are positive. And in the bottom left graph, all the slopes are negative, meaning that all the flight conditions satisfy the static stability requirements. Again, on the plots on the right signify the control power of the control effectors, meaning that the vehicle is still able to steer itself without being too stable. Next slide.
For the aerothermal analysis of the aspiration, more questions must be answered. How much heat will be generated? How hot will the skin of the aircraft get? And will this be a limiting factor for trajectory? In order to answer these questions, some values must be known, like the flight conditions and the geometric properties of the aspiration. These will allow for the output of the overall heat flux into the skin, or the energy applied at the surface, and the temperature history of the flight phase. Next slide. A transient temperature estimation tool was developed that uses the balance of energies in the flow and an arbitrary body with known material properties to yield a temperature history of the input flight conditions. The method relies on the idea that high-speed flow will compress, heat up, and apply convective heat to the surface. The temperature of the surface is then validated with a measured temperature history of the X15, and this shows accurate peak values and rough transient accuracy. Next slide. Using the validated transient tool, a part of the aspiration may be analyzed under a calculated trajectory analysis to get an idea about peak temperatures and heat flux throughout the flight. This shows the result of such an analysis with the start at the front of the climb phase and ending with apogee. This analysis shows an ability to withstand climb easily without considerable compromise to the current model. Next slide.
Looking back to those FAR 25 regulatory requirements, the climb phase needs to have a climb gradient above 91.4 meters per minute since it weighs above 2,721 kilograms. It has a climb gradient of 289 meters per minute, so that's way above. And once again, the aspiration passes with flying colors. With this verified, we can now evaluate the coast phase.
Passengers are reminded to please sit back with your chairs in the upright position to avoid redout while we propel you vertically to Mach 3.2 with the main engine cutoff at 40 kilometers. For your pleasure and comfort, we will maintain acceleration with our Merlin 1D rocket below 3 Gs for the duration of the climb.
Now transitioning over to the coast phase.
The trajectory analysis of the unpowered coast is arguably one of the most important analyses throughout the mission profile, as this is the experience the customer is paying for. Consequently, critical questions like how long will the microgravity experience last and what will the apogee altitude be needed to be answered. The goal was to achieve a higher apogee altitude and a longer unpowered coast time with respect to Spaceship Two and other space tourism companies in the market. Next slide. The unpowered coast analysis was performed using the projectile motion analysis as the vehicle mass is constant and no thrust is being generated. The unpowered coast analysis indicated that aspiration experiences an apogee altitude of 111 kilometers with a time to apogee of a little more than 110 seconds, which results in a total microgravity time of about 4 minutes due to the parabolic behavior. Nominal trajectory analysis of Spaceship Two indicated that the vehicle reaches an apogee altitude of 103 kilometers with a time to apogee of around 100 seconds. Consequently, customers, now astronauts, flying with aspiration, will reach higher altitudes for a longer time. Next slide.
Due to the rapid drop in air density above 40 kilometers, conventional control surfaces lose their ability to provide pilots with the control of the spacecraft, so we must rely on a reaction control system to augment control power. Here we can see two animations. On top is Boeing Starliner demonstrating the use of reaction control thrusters, while below we see the 3 axes with which aspiration must be controlled: roll, pitch, and yaw. On the left, we see the moment arms created by the placement of the reaction control system thrusters, which, due to the placement of the yaw thrusters, has become coupled with the roll axis. Based on design criteria for the X-15, the desired angular acceleration rates were chosen, and from those rates, the required thrust force was derived.
Like Ben mentioned, RCS thrusters are used in spacecraft to enhance the level of control. The CHT-400 is chosen because it is a lightweight, it is small, and has one of the best thrust-to-weight ratios compared to other thrusters. As can be seen from stability and controls, 2 thrusters are placed on each side of the nose on a basis of 3,500 newtons of need. For pitching and for roll, they're placed on the side in front of the wings. Producing 400 newtons, multiple of these thrusters can meet the control requirements, which has been found to be better than implementing one massive system. It has flown more than 30 times with the Ariane 5 during its ascent phase, which can weigh up to 170,000 kilograms, which shows us its reliable system. Next slide.
Ladies and gentlemen, on behalf of all of us here at Reach Sub-Orbitals, I would like to present to you your commercial astronaut badge in recognition of your intrepid exploration of space and the final frontier. And in addition to exceeding the von Karman line, please feel free to float about the cabin and enjoy the magnificent and breathtaking view of our beautiful blue planet.
Now transitioning over to re-entry.
A huge role in the re-entry phase, aerodynamics makes up 2 of the 3 forces acting on aspiration during the unpowered flight half of aspiration's journey back to Earth. A big factor in the re-entry analysis is whether or not the vehicle produces enough drag during re-entry in order to slow the vehicle down enough before landing. The analysis methodology IDA to quantify this was solidified across a semester of research. Next slide. The analysis methodology was verified to show good agreement between analytical methods and known data. The lift and drag of the vehicle was calculated as a function of altitude. This showed aerodynamic effects beginning to only start to affect the vehicle at 75 kilometers. Next slide. From here, the important aerodynamic parameters were calculated. The lift, drag, and aerodynamic efficiency profiles were calculated for the trajectory of re-entry up until glide. Drag reaches its peak just before the pull-up maneuver where the glide phase begins, bleeding off enough of aspiration's energy for glide and landing. Next slide.
The re-entry trajectory phase aims to answer critical questions such as what will be the maximum G's experienced by our passengers and what will be the duration of the re-entry trajectory. To the right is the re-entry IDA methodology influenced by John Adams' atmospheric re-entry research. The IDA helps answer the critical questions where the main inputs for the re-entry phase is our vehicle's dimensions and weight, entry velocity, and aerodynamic coefficients. The primary outputs are various performance profiles. Next slide. Beginning from apogee, our vehicle behaves like a point ballistic mass in free fall. Using the empty mass, reference area and length, and drag coefficient, the ballistic coefficient could be found, the primary parameter driving ballistic reentry. Coming in at an 81-degree flight path angle, speed and load factor begin to rapidly increase. Roughly 35 seconds in, our vehicle has gone from 75 to 45 kilometers, now at Mach around 3.4. Next slide. Switching from pure ballistic entry to a lifting entry, our vehicle begins a pull-up maneuver. With speeds reaching Mach 4 and plunging into the denser parts of the atmosphere, our primary goal is to stay within the 5G constraint for the safety of our passengers. After 60 seconds and experiencing a maximum of 4.8 Gs, during pull-up, we have descended down to 7 kilometers, concluding the re-entry trajectory. Next slide.
During the re-entry phase, the pitching, yawing, and rolling moment coefficients plotted against angle of attack and side slip angle are shown in the following plots for 4 flight conditions. The moment coefficients with respect to elevator, rudder, and aileron deflections can also be seen on the right. These plots represent the control power of the control surfaces. These stability plots were generated using aerodynamic data. Since all static stability criteria is met, we can say that the aspiration is longitudinally, directionally, and laterally stable for all flight conditions during the re-entry phase. Passing the presentation off to the next discipline.
This is the aerothermal reentry IDA. It outlines the analysis process that was followed for calculating the heating during the reentry phase. The inputs are the flight profile and the vehicle geometry. The key heating parameters that must be estimated are the maximum temperature and heat flux. Next slide. An analytical tool was developed and validated using X15 flight disk data. This tool estimates the heating and it is compared to resolve the error. The error was found to be between 6 to 11%, which is well within the estimated values for the tool. Next slide. A trajectory heating prediction was developed to estimate where the top heating occurs along the trajectory. It was found that the maximum temperature was 500 degrees Celsius at around 15 kilometers and a Mach number of 3.8. Next slide. The transient analysis shown here accounts for the heat being dissipated as time progresses. This is a more accurate method than the one shown previously. With this method, it was estimated that the maximum temperature would be 465 degrees Celsius, and this would occur about 350 seconds into the flight. Next slide.
As a benefit of moderate Mach numbers, aspiration endures relatively low heating and thus requires only a simple thermal protection system. The material chosen was the NASA Advanced Flexible Reusable Surface Insulation, or AFRSI. AFRSI offers a number of advantages when compared to other options. As a lower temperature TPS material, it is easier to maintain as well as install. There are no tiles to worry about either since it is a woven fabric. Based on the data received from Jared and Josue from Aerothermal, a worst-case heating scenario was made and the TPS material thickness was sized accordingly using one-dimensional analytical techniques. Next slide.
Now for the most heart-racing, blood-pumping, and exhilarating moment of our adventure as we hurtled towards the Earth at the breakneck speed of 1,200 meters per second, we approach the 4G pullout. Ensure your seats are fully reclined for proper G orientation. Relax and enjoy the rush.
Transitioning over to glide.
For the unpowered glide phase, all the fuel and oxidizer are depleted. Therefore, the center of gravity location will not shift significantly after engine cutoff. Center of gravity location is a function of the component weights and the component locations. For the x position of the center of gravity, it's measured with respect to the nose, and the z position of the center of gravity is measured with respect to the bottom of the fuselage. The center of gravity location and body inertias for the aspiration for the reentry phase are shown in the tables below. Passing the presentation off to the next discipline.
This is the aerodynamics glide IDA. It outlines the process used to estimate and validate the glide profile. The inputs are the flight profile and the geometry in order to estimate the aerodynamic properties. The key performance parameter to verify is the glide trajectory with the available aerodynamic performance. Next slide. A numerical tool was validated to accurately predict the aerodynamic properties for the vehicle at multiple flight conditions. Next slide. An aerodynamic database was developed for multiple flight conditions, and the control surface deflections were also modeled for the stability and control and trajectory and performance disciplines. Next slide. The glide trajectory is primarily dependent on the lift to drag ratio. An analysis was performed to determine whether the desired trajectory was feasible. As long as the black line shown in the figure on the right remains on top of the colored surface, the glide trajectory is feasible. And as can be seen, the glide will be successful. Next slide.
The unpowered glide phase aims to answer questions such as at what rate will the vehicle descend, what will be the duration of the glide, and what is the maximum range through the glide phase. To the right is the IDA methodology influenced by text from Roscoe, Phillips, and Nicolai. Using the IDA to aid in answering the critical questions, vehicle dimensions, previous flight phase conditions, and aerodynamic coefficients are all inputs required to output the altitude profile, vehicle glide range, and rate of descent. Next slide. Continuing immediately after its pull-up maneuver, the glide phase begins at an altitude of 7,063 meters with a Mach of 0.8. To meet its target altitude of 200 meters, the vehicle's lift-to-drag ratio is used to minimize the rate of descent, and its flight path angle is used to maximize glide range. Throughout the glide trajectory, the vehicle's flight path angle changes ever so slightly, ranging from 4.5 to 5 degrees, achieving a rate of descent of 12 meters per second and a maximum glide range of roughly 85 kilometers. After 11 minutes, the vehicle slows to a Mach of 0.2 and reaches an altitude of 200 meters, reaching its target altitude and velocity, concluding the glide trajectory. Next slide.
During the unpowered glide phase, the pitching, yawing, and rolling moment coefficients plotted against angle of attack and side slip angle are shown in the following plots for 9 flight conditions. The moment coefficients with respect to elevator, rudder, and aileron deflections can also be seen. These stability plots were generated using aerodynamic data. Since all static stability criteria is met, we can say that the aspiration is longitudinally, directionally, and laterally stable for all flight conditions during the unpowered glide phase. Passing the presentation off to the next discipline.
Fellow astronauts, it has been a pleasure and an honor to spacewalk with you here today among the heavens. We will soon be landing, but for now, we ask that you take a moment to relax and reflect upon the astonishing experience that you have partaken. From this day forward, when you look up at the stars, you will know they will always be within reach. With reach, suborbitals.
Now transitioning over to the landing phase.
Once the landing gear is deployed, the center of gravity location will shift, as well as the body inertias. Upon deployment of the landing gear, the center of gravity shifts back and shifts down slightly. Also, upon landing gear deployment, the body inertia about the rolling axis increases, and the body inertias about the yawing and pitching moment axes decrease. The center of gravity location and body inertias for the aspiration during the landing phase are located in the tables shown to the right. Passing the presentation off to the next discipline.
This is the aerodynamics landing IDA. The inputs are the flight profile and the vehicle geometry. The key parameter to estimate are the ground effect and the landing gear implications into the aerodynamic properties, and to ensure the wing is correctly sized for landing. Next slide. The main aerodynamic parameters are estimated with the same tool as for the glide trajectory. However, when the vehicle flies very close to the ground, it experiences a lift increase and the drag decrease due to ground effect. The model shown here can correctly estimate the ground effect aerodynamics for an F-15 based on its flight test data. Next slide. The ground effect does not become significant for a vehicle until a height of about 5 meters off the ground. This ground effect causes a 26% improvement in aerodynamic efficiency. As far as the landing gear goes, that drag was estimated based on existing vehicle data. It was determined that when deployed, the landing gear will exert a 15% increase in the total vehicle drag. Next slide. The actual landing procedure is a very delicate balance of weight, aerodynamic lift, and airspeed. The analysis shown here was developed to help understand how changes in vehicle weight and landing speed can affect different landing capabilities. As is shown in the figure, aspiration has a wide range of landing scenarios. Next slide.
Hi, in the landing analysis for trajectory and performance, some crucial questions must be answered, like the approach velocity and the landing field length to bring aspiration to a complete stop. Therefore, on to the next slide. The landing phase analysis for aspiration is determined right after the end of glide flight. The components needed to begin the approach need such variables such as lift and drag forces upon the vehicle. This can be determined by providing a Mach number, angle of attack, and altitude for the vehicle. In doing so, in my analysis, aspiration starts its approach at an altitude 200 meters above the runway. Aspiration has an approach velocity of a Mach number of 0.22 at an angle of attack of 14 degrees. The next part of the landing phase is the flare maneuver, which is going to start 238 meters away from the runway. Once at touchdown, the vehicle is going to slow down to a speed of 66 meters per second. After this, the aspiration will start its free roll of 200 meters, and then the brake system will kick in. Therefore, the aspiration braking distance will be 367 meters long around the runway until it comes to a complete stop. In the upper right-hand corner describes 3 situations of what the landing could be, but a best situation is posted as good on the table. On to the next slide. The trajectory analysis for all the mission phases were collected by TNP lead engineer Henry to show the total trajectory of aspiration. Now on to the next slide for certification.
Confirming Pablo's work, the final certification of the aspiration is completed with the FAR 25 regulatory requirements for the landing phase. Velocity at approach and touchdown must be small multiples of the stall velocity, and the landing distance must facilitate a clearance of 15.24 meters. As can be seen, aspiration is a fully certifiable vehicle according to FAR 25. Next slide.
The IDA for cost, safety, and certification are combined into one master IDA to ensure that the design point follows all safety certification protocols while ensuring the an affordable space tourism experience. To estimate how much that space tourism flight costs, the TransCost model was used to determine its direct operating costs, the development cost, manufacturing costs, as well as operating costs. The TransCost model was used, and the Spaceship 2 data was used to validate or verify those methodologies. The TransCost model provided promising results. We first calculated the airframe development cost along with other manufacturing costs, and since we were buying a commercially off-the-shelf engine, we didn't need to develop an engine development cost. According to that figure, you can see that the break-even points are shown according to with the number of flights on the x-axis and the revenue being generated on the y-axis. The break-even analysis gave us results that said that the number of flights, if for one aspiration flight, if we fly that one aircraft for around 1,500 flights for a ticket price of about for $200,000 per seat, will break even in 1,500 flights, and the launches per year rate was set to 220. And that concludes our presentation. Thank you for listening in today, and that's about it.
All right, everybody, let's again unmute the microphones and let's reward this team with a round of applause. Thanks so much. All right, So I think we are realizing that we have had an unusual presentation at the rear end here with team number 3. Surely the balance of technical and a real customer closeness forecasting into how you would experience, right? So what we like to do is we like now to take any questions from our audience before, in a second step, how the teams start maybe to engage amongst themselves in a Q&A on more technical detail. So now we have an opportunity to see Monica. Greetings, Monica. Go ahead with your question, please.
Hello. My question is specifically for the Reach Sub-Orbitals team. I noticed that your configuration has multiple windows. Did your team consider how the size and number of windows would affect the pressurization inside of your cabin throughout your mission? And if your windows one of them were to be blown out, how would you mitigate losses, pressure losses inside of your cabin?
So we were initially considering a lot more windows than 18 windows that we have for our design point, and we were basing this off the geometry for Spaceship 2 and other re-entry vehicles that we were looking into, and that's how we decided the number of windows. And I'm pretty sure geometry and weights, they all came to the same conclusion that if we decided to go with more windows, it would be structurally unsafe. And we got the same instructions from our TA. And yeah.
Well, maybe in this context, excellent question, Monica. Which team did consider the design of a pressurized cabin, actually? What effect it would have on the weight? And by the way, of course, since the cross-sectional choice and the difference between the 3 teams hasn't been compared, right? Because there were 3 distinctly different cross-section choices. What has been the take on pressurized cabin? Has this been considered? Let's start with team number Albatross.
So I believe that the internal cabin pressure, it was mentioned, but it was not considered if there was a window blowout or if there was some depressurization event that occurred.
Yeah, I agree with that, but the question has been whether the structural design of the cross-section did consider basically the sizing of the pressure vessel for the passengers.
I do not believe that was considered. That would be more of a question for our weights person.
Structure weights from Albatross. Any comment? So I guess we take this as a no. Team Helios.
Yes, sir. I'm going to have to pass this question down to my structures person as well.
Yep.
So the weight of the pressure cabin was not considered in terms of how they would affect the total weight of the vehicle.
Yeah. Team Reach.
That the pressure effects of the pressure cabin on the structure were not considered. No.
Yeah. Okay. It's a good point. Remember, especially Team Reach, you focused on the passenger, on the customer. You should have presented a very different, appealing presentation by animating, by giving an experience, by having a very clean technical build-up, and switching from the operational experience emulated towards back to the technical. So very, very interesting style you have chosen, right? Which surely in terms of technical entertaining is surely, you have been setting the bar pretty high for future Capstone to come, I can imagine. All right, well, we are taking questions from the audience. Maybe we have senior design 1 members there. I've seen that we had earlier Dr. Amanios. Usually he's asking about structural design. Maybe we are off the hook.
Hello, I had a question to the propulsion discipline on the first team that presented.
Oh, this is Tony, right?
I believe it was Biley that presented. Do you believe that the RL-10 was the only engine capable of completing the mission? What other engines did you look at if you did? And I noticed that the other teams selected the Merlin. So can you give reasoning for that?
Yeah, so definitely the RL-10 wasn't the only, I wouldn't say it's the only engine capable, as the other two teams did use variations of the Merlin engine. But for this vehicle, it is very important that we have an engine that is both, it's lightweight, it can also complete the mission. And I think just comparing the engines, just from what I know in my database, the RL-10 is about 168 kilograms, so that's like 370 pounds. And the Merlin's a very heavy engine, it's around 1,000 pounds. So we didn't want our vehicle to be too heavy. So our team decided to go with two of the RL-10 engines, which still kept the total weight of the vehicle down. And then you also asked, what other engines did I take into consideration? We wanted to hold the rocket-based combined cycle as a trade, mainly because it's using an air breather at a lower Mach number, and that increases the performance about 15 to 25%, which Virgin Galactic, with their White Knight 2 Spaceship 2, they have that performance advantage. But mainly the objective of the project is what engines can we use that will put us in the first generation space tourism companies. So the rocket-based combined cycle would require more like research. And so we just looked at the engine database, chose the RL-10, it's lightweight, it's throttable, and it has a high rocket performance. So we did believe that was best. I hope that answers your question.
Yeah, thank you.
Yeah, very good question, very good answer.
Follow-up for that propulsion, because yeah, the RL-10 is a lot lighter, and we were considering that engine. The issue we ran into and the trade-off that we saw, and I guess I'm asking if you considered this, is that the RL-10 had a thrust-to-weight ratio of 40, while the Merlin engine has a thrust-to-weight ratio of about 140. So that's something that I'm asking if you guys considered. And additionally, did you take into account the thrust differences at altitude and at sea level? Because that was the other issue we ran into, is that initially, propulsion was only considering vacuum thrust, if I remember correctly, but when you take into account the progression through the atmosphere, the RL-10 loses a lot of performance. So I guess, did you consider that?
Yeah, so basically we did, when we were using the RL-10 engine, that is something that we considered, just because we thought after it reached a certain altitude, performance would be it would decrease, a little drastically, but the thing is, just because we were more so considered on weight and trying to get a final sized vehicle, we were looking at just what thrust requirements we were getting from performance and aerodynamics. So just because the numbers that we obtained were a little low for takeoff, about, I believe it was 60 kilonewtons, and then max of the boost that we got from performance, the value that I was getting was around, I think it was 142. So since we knew that the thrust available on that engine was about, I think, 99 kilonewtons, we said, okay, should we throttle the engine at boost phase, we can still be able to meet the thrust requirements. And I did show that on the graphs, both at 50% at full throttle, they still did meet requirements. So we went ahead and went with it just because we still wanted to go ahead and keep the weight down. That was the overall, that was kind of our trade-off there. But that is a great question. And yeah, that is a good question.
That makes sense. Thank you.
Mm-hmm.
I had one other question for Albatross aerodynamics.
Wait. Let us first.
Let someone else.
I know. This is beautiful. This is already, the teams are heating up. That is wonderful. Let's pause this for a second, because let's give our audience an opportunity to ask questions. So our audience. So, well, which team do you like to put your money down? Right? Surely would be a question to ask. So anybody from the audience who likes to ask another question of any sort?
I have a question for the chief engineers. I'm just wondering what the biggest challenge your team faced throughout the course of the semester was for each of the chief engineers.
You might identify yourself quickly.
Oh, I'm Arthur Koster. I was a chief engineer for Weatherman Aerospace in the summer.
Wonderful. It's nice meeting you again.
Do you guys mind if I go first?
Go ahead.
By all means.
Arthur, thank you. That's a very nice question, actually. If you're considering non-academic challenges, it was pretty much just organizing meetings, getting together on the same page. The flow of information wasn't as fast as in-person classes, obviously due to the current situation. That was one of the main challenges where people were considering different versions and there wasn't enough communication. That was one of the challenges. If academic challenges or challenges related to the project are concerned, it was maintaining a balance between like all aircraft sizes methodologies go. It was maintaining a balance between getting that thing off the ground, especially for our project, our geometry. Since it was an all-body geometry, we had to generate lift with our fuselage, and that meant that we had to either rely on getting up to higher speeds on the takeoff during the takeoff phase, or having a more sleeker aerodynamic profile. So those were some of the challenges that we were considering, but thank you, that's a great question. I'll let other chiefs answer.
All right, I'll go ahead and go. SK pretty much covered most every issue that there could be. And as far as teamwork goes, it's really a whole lot of getting everyone together on the same page and getting data going like that. I would say for me and my team in particular that the biggest...
Is it possible to use a camera by chance?
Are you asking me? I can, yes.
Yes.
Yeah, sure.
Wonderful. Right. That's much nicer.
All right, so for my team in particular, there really wasn't any issues in terms of getting data between the disciplines. The overall, I would say really the biggest issue that we had was just scheduling meetings on when everyone was available for certain last minute things, you know, for like the week before midterm or the week before this presentation, all the last minute stuff that needed to happen, trying to get everyone available at certain times to have more meetings per week than we normally did, and just overall finding the time and way to get everyone on the same page when things change hour to hour, is making sure everyone's updated and keeping that consistent. So that was probably the main issue that we had this entire semester, honestly.
Yeah. Okay. Helios?
Yes, so the main problem with our team was communication, like the other chief engineers have said.
Camera, please.
Oh, yes. So our biggest concern was teamwork and organization. And from a synthesis perspective, it was just integrating all the different disciplines and making sure that we got our configuration to come out the best that we possibly could.
Right. Thank you so much for the question. I mean, that is surely at the heart of the activity, because remember, it's a very different class. It's number one, it's open-ended. I'm not controlling individual output. You have to be self-motivated. The chief engineer suddenly becomes the surrogate boss along these lines, making sure where are the weak links in the chain, because there are always weak links, which can be attributed to personality, to technical, to COVID, to electronic, to everything, right? And by the way, we don't want to utilize COVID as an excuse or distance as an excuse because we will find, you will find in your future employment situation, awkward situations overall. You always have to maneuver. You have to learn to maneuver, to be mobile, to still make it a good looking and a quality success overall. given those conditions. So you may have seen Ian Marks, a former Capstone student, going through the same procedure. Now at Lockheed Martin is asking a few questions. Number one, whether supersonic drag analysis has been done on the vehicles. Maybe let's start again with Team Reach for right now. Remember, maybe you first quote what is the maximum velocity your vehicle is experiencing, and to what degree supersonic aerodynamic analysis has been done. Team Helios.
I will let my aerodynamics chief get that question.
Yep.
Jared, I'm gonna have Jared is our supersonic person.
Yeah. You can hear me okay?
Yeah.
Okay.
And we can see you. Wonderful.
Perfect. I actually did just type it. I wasn't sure if you're going to address the chat.
Yeah.
But yes, we made sure that the cross-sectional area throughout the length of the vehicle was somewhere between a Sears hack body and a Von Karman ogive, since we needed to have a relatively flat base for the engines. So we couldn't go all the way to one or all the way to the other because of our constraints with volume. But so we put it was relatively close to a Sears hack body in the VSP model.
So you considered area ruling? You checked that?
Yes.
Yeah, Jared's being a little putting stuff lightweight. He did a very in-depth analysis in VSP Aero. We had the geometry team do an area ruling calculation, which we validated with the VSP Aero calculation. All of this to ensure that the specifically supersonic, but more importantly, the transonic drag was correct based on the open VSP Aero data.
All right, Team Helios.
Yes, so I know that our team did incorporate supersonic drag buildup. I'll pass this to our aero team to answer that question.
And video, please.
Unfortunately, I can't turn on my video at the moment. I'm not in a location where I can do that. But for supersonic, I try to work with the geometry team and get the area ruling done using OpenVSP. We ran into little complications. The way we try to go to minimize the supersonic drag as well as transonic drag was with highly swept delta wings. Through literature, we found that that a subsonic leading edge would overall reduce the wave drag throughout the transonic and the supersonic regime, and obviously the drag reduction was done in order to maintain some level of excess thrust throughout the power descent phase in order to minimize the propulsion system needed for the power descent.
Right, wonderful. Team Albatross.
So again, I will defer to aerodynamics for the first question.
Yeah, so as part of the aerodynamic analysis, like on the reentry, for example, we did do supersonic drag analysis, and the primary method used for that was one outlined by Kuchimon. And so that was considering a couple different variables, including like the skin friction drag and the vortex drag and the wave drag and things of that nature. So that was part of the analysis as well for our team.
All right, well, let's move to Ian's second question, or surely something I noted myself by poking you. He's asking for the turnover angle, which is of course part of landing gear positioning, etc. Let me ask simply. It looks like the Team Reach did discuss landing gear design explicitly. Team Albatross didn't show that much. Team Albatross, did you do landing gear design?
Yes, we did landing gear design and placement. We also did an analysis for turnover angles as well as the maximum speed. You could turn the vehicle before it would do a turnover. I do not know the answer to the question in like the exact speed or the angle you could turn at. I do not know that. All I do know is that it did pass those checks that we did perform.
Yeah, and since we are Team Helios landing gear design.
Yes, so we did incorporate a landing gear design. As far as the question of the turnover angle, I would have to deflect that to our structures person who did that.
Is he still there?
Yes, so the overturn angle for us is actually 56 degrees. According to Roscom, a safe maximum limit would be around 57 to 55 degrees for the overturn angle for a non-carrier based aircraft.
Okay, let me add to this question a Chudoba question. How many wheels do you have on the nose gear on each main gear?
Helios has one tire for the nose gear and then one tire per strut for the main gear.
All right. What about the other teams? Before we comment on that.
Pablo, you're up.
Yeah, I'm right here. For the nose gear, I sized 2 tires for the nose gear and then 2 sets of 4s for the main gear. That was due to the factor of safety. If one of the tires were to pop, the other tires will take on the load required for the main gear and the nose gear, which the nose gear was for 10% of the load and for the main gear 90% of the load. And I also had to account for, when sizing the tires, how fast the vehicle was going. You don't want the tires to heat up and burst along the runway. Yeah. So yes, I took account on that. And also to Ian's question of the overturn angle, within the slide, I actually showed parts of analysis for that overturn angle, and I showed how that was calculated.
Okay, team Helios, landing gear.
Yes, so our nose gear carried 11% of the load, and then the main gear carried about 89% of the load. We decided to go with one tire for weight reduction and cost reduction, and also volume reduction as well.
Yeah, I'm getting a little scared, of course, with a single tire situation.
Yes.
It is something, what about when that tire blows, right? I'm not sure whether the FAR nor the passengers are that happy that you're deviating from some good standard airplane design has experienced, especially since this is rather considered a high performance vehicle. Let me add on to the Chudoba question, the Chudoba square question. Anybody did consider, because I believe that you have retractable landing gears, right? I assume that nobody said anything, that these will be retracted into something. Anybody did consider the volume that it actually fits into something in the volume?
Yes.
Okay.
Yes.
Sorry.
Yeah, no, it's fine. It's fine. With the landing gear size, and we know how big the landing gear had to be to clear a 16-degree angle of attack. We knew how long the landing gear should be and how much volume, based on how wide the tires were separated from each other. We calculated a volume set within the. That was one of our main issues, to find the main volumes within the aspiration to be placed with everything else along with inside the aircraft.
What about Team Helios?
NK was able to determine the volume.
We did consider the volume of the landing gear with the placement of the tanks. Sorry.
Yeah. Okay. Team Albatross.
So we did have a goal of determining the landing gear volumes. I'm not sure if that got calculated or not. That was for the landing gear people. Do you all have any answers on that? I'll defer to them.
No specific figures, but we did account. We're thinking about adopting the same plans that the Lynx uses, where they have their landing gear, retracting in the same way they do, and it would just scale up. Whatever volume they allocate to landing gear would be similarly scaled up for our model.
Yeah, okay. So looking at Ian's third question, let me modify that because I got a little bit ticked off on Team Albatross at the beginning, because in side views showed a reduced order model where you showed the extreme center of gravity positions. I'm not sure whether they were really that far apart. Now, when you lay out such a vehicle, and Team Albatross, you had, of course, the cabin up front, and as you expressed it, you had the fuel in the back end, right? So when you are utilizing the propellant, which is the oxidizer and the fuel, the way how are all three teams balancing the vehicle, because it was primarily Team Reach at the end, which was very nicely claiming that the vehicle always has been nicely statically stable throughout. Not everybody had that situation. And of course, it depends on how you balance the vehicle, whether you are keeping the center of gravity restricted, but it looked like that, especially Team Albatross, I recall at least, the center of gravity was excessively moving, of course, resulting in a lot of follow-on problems. You remember we talked maybe in class about the Skylon problem. Go ahead.
So I knew I should have changed it before we presented, but the reduced order model there was 4 CGs listed. One of them was the takeoff weight, one of them was the empty weight. The forward CG and the aft CG were the absolute limits that were calculated for them. That was not the actual values that were determined. The center of gravity for takeoff gross weight and empty weight, those were well within a meter of each other. For the placement of the actual volume propellant tanks, those were supposed to be centered in the vehicle, in the center of the vehicle. That way the CG would not vary that much between burnout and takeoff. And it worked rather well from the results.
All right. Yeah. Good answer. Good answer. Okay. Team Helios, did you consider the overall balancing and positioning of the cabin layout with the propellant tanks? Because to some degree, of course, flying supersonic and then subsonic in those extremes, yeah, you have neutral point shift. And how did you consider marrying those or limiting some of the trim changes?
Yes, so we did consider that. I was just talking with our aero team and our structures team to get this figured out. I'll refer the question to them.
Yep.
So to get we did initially run into some problems with having the the propellant tanks further aft in the vehicle. We found that the center of gravity was sitting behind the aerodynamic center, which would make the vehicle unstable. We then decided to add we considered somehow moving the propellant tanks forward, but due to the geometric restrictions, there was no place for them to place it. So we had to add a small amount of ballast towards the front end of the vehicle to balance it out.
Okay, did I bypass Team Reach, the third team? Which one did not comment on this issue of balancing the vehicle? I mean, that's a primary thing, right? You're using a propellant. You want to be stable and controllable as good as it happens, or as good as it can be. The third team.
Yeah, I'll take that. So one of the first things we did whenever we were in configuration layout is that the weights team was almost on every iteration calculating empty CG, full CG, whenever the fuel was moving around. And especially since we were considering 2 different fuel sets that had a significant difference in volumes and the CG shift. So that was getting checked almost every time. And then whenever we went into configuration evaluation, part of the aerodynamic process was using both the empty and full CG when we were calculating all the aerodynamic data to make sure that for no matter the flight condition, no matter the fuel volume or fuel weight that was in the vehicle, that we were statically stable. And I mean, the results show we're always statically stable.
Okay, good. Final question from Ian. Anybody did consider a safety issue? That how can you actually place fuel propellants in relation to a commercial passenger? It's something the airplane designers experimented with. When I remember when being involved in a hydrogen airplane study, that there were a lot of Airbus studies where the hydrogen tank was placed on top of a traditional Airbus plane. And certification surely didn't like that idea in a crash landing, that suddenly hydrogen is raining down on you, right? So that's probably what Ian's question here is relaying. So since none of you were able sort of to put the fuel into the wings, right, to put it away from the passengers overall, anybody considered that thought in terms of safety?
Yeah, Reach Sub-Orbitals considered, I'm sorry. Reach Sub-Orbitals definitely considered that as a thought, but the best that we could do is place it pretty much as far away towards the back while still allowing for stability control. Along the center of gravity and not too much of a neutral point shift.
Fair answer.
Yeah, allow for cabin space. And in the design, we included a back wall in the cabin to kind of at least keep some sort of buffering between them.
Yeah, I mean, remember there's a pressure vessel and there's a pressure dome, and most likely, right, these are two separate systems overall. All right, any other questions from our audience? I was intrigued by the last team talking about the break-even point, which was calculated by how many flights for a single vehicle to reach the break-even, which is usual, but usually break-even is how many airplanes do you have to produce in order to reach the point of making the first black dollar. Anybody did the, go ahead.
Oh, sorry. So I was going to say that before we did that, the three chiefs agreed together that to create a better, create a direct comparison between all the three teams to see which one's more profitable, we decided to agree on a set launch rate per year. So, and we decided to include one flight vehicle in this entire estimation. So that's all I wanted to say.
Question for all three teams, since it looks like universally you use transcost. How applicable has transcost been actually? Did transcost ever consider a tourism mission in their cost buildup?
So transcost was mainly for made for orbital vehicles, but there is a version of transcost. It's called Sub-Orb transcost. We did also consider that, but that methodology seemed to deviate from the results that we're expecting, the verification results. So we didn't use that too much. But there is a version of transcost, but also the document, the book for that is relatively old. It was written in 2002, and the latest version of transcost was published in 2013. So that gave us a little more confidence, especially with verification, for us to stick with that that methodology.
Yeah, but I guess the publication date is due to revisions done by Dietrich Köller in his text. So not necessarily that he was, I don't think he was considering adding the fledgling space tourism vehicles into his tools, right? He did not.
He did mention the Virgin Galactic vaguely in the text in the latest version, but he did not provide a full-on methodology for suborbital vehicle. No.
Yeah. Okay. Good. Any further questions from the audience? Come on, let's enjoy the fun. You have three groups, three specialist groups. Ladies and gentlemen, let me say something here in between. Remember 2 semesters ago, when you started senior design, you didn't quite know what is happening. And here we are on your final presentation date. By the way, it's still the date before your final report submission, right? So you still have a lot to do probably with your final reports, where the truth is in, right? The truth is in the final report. But please remember the performance you all created today and how you're now able to address the specialist questions, most likely, what will happen now. What a difference 2 semesters and learning and some pressure and motivation most likely does for you being able to basically show some proficiency in these fields, because 2 semesters ago you had more or less zero idea about supersonics, nor about rocket engines, nor about any of these topics, TPS, etc. So congratulations for staying persistent and going through all of this. It has been an uphill battle, I can imagine. Right. Any question from the audience? Because if this is the case, then I like that the three groups are a little bit chatting with each other. The ground rules are, because we already had questions for each other, the ground rules are we want to be very professional, right? We don't want to ask questions below the belt, technically, to just expose and enjoy, etc. So we have seen 3 teams of different style, of different presentation contents, etc. That's the beauty. Remember, we are still one company here, right? Representing UTA. It's like the red, blue, and green team. And now it would be, of course, wonderful if we would have another semester to continue refining and add you into one big team. So again, I'm staying out of this, adding another semester. I think 2 semesters have been good enough, getting you out of the door, most likely. But let me kick this off in terms of synthesis. Remember, the whole thing starts with the synthesis work, right? Go ahead.
Before we proceed, there is another questions about ticket pricing in the chat. I would like to address that. Stanila asked, are the ticket pricing competitive to what Virgin Galactic would charge per flight for space tourism? For Albatross Spacelines, we did come up with that result. We did verify that because Virgin Galactic right now has tickets set at 250,000. We did an analysis and we had quite a large range initially between 150,000 to 300,000. And then we did a break-even analysis to determine what price, like to I guess to specify what price would allow the company to generate a profit, but also is competitive with the other companies. And our ticket pricing as Albatross Spacelines was set to 225,000, which is slightly lower than Virgin Galactic due to the fact that we only have a single stage system. So cost factors in terms of like operating costs. Since Virgin Galactic has that 2-vehicle system, they have to operate 2 different vehicles compared to us having only 1 vehicle, which allowed us to reduce our tickets prices slightly.
I mean, could it be that some of those ticket prices are substituted by the rich owner? That these are not the real costs of the tickets which are charged, but in order to keep it floating, keep it alive, that there's some, not government substitution. We're not talking about the bailout plan. I don't think this is what is happening here. But did you take this into account, that maybe this type of industry is fledgling based on the investment the organization is pumping into, right? Maybe they're not asking the real price. Could that be true? Did you think about that?
Yes, we did consider that. The thing about Virgin Galactic is it is a public company, so they do have a lot of investor information out there. So yes, we did consider the fact that it could be more warranted towards the investor, maybe. So yes, that was a thing we'll consider.
Good. The other teams.
Oh, sorry. I didn't realize. Okay. That is, we didn't have the same approach as Albatross Spacelines. We did not consider the fact that they were doing that, and we didn't consider the fact that they were open to their investors. We did use some of their published materials for our analysis, which was helpful, but as far as transparency goes, we did not consider that.
Good question, good answer. Because you would be rational, you would really see what's the hardcore business case overall, because even those .com millionaires or billionaires, of course, at some points, it's like Richard Branson, he already is selling shares already in order to stay afloat. So even although you may be rich, there's a limitation to how rich you have to be in order to keep things going. It's only this other company, right, SpaceX, which right now has the richest man on the planet, which, by the way, is a novelty in aerospace. You know, when I was your age and in school, there was this saying, if you want to make a fortune, right, you don't start, you cannot do this in aerospace, right? And it's quite interesting that we have now an owner of an aerospace company which does do radical design, radical breakthrough, and at the same time, he's the richest person on the planet, which is quite a novelty you guys are experiencing with that. Okay, so do we have another external question? Thank you, Stanila. Let's switch to a conversation between the synthesis people right now. Let's start from the beginning, where challenge yourself to what degree the verification, the solution space topography, the baseline design you have been picking has been meaningful. And of course, what I missed sort of was to instruct all three teams to maybe have a combined slide at the end where you're possibly comparing the designs, which would be of course useful, and where you discuss the cross-sectional choice and some of the practical configuration layout differences which come with it, right? Remember some of the configuration layout, the geometry, the sizing, giving it a shape, it was not quite clear what's the difference between the wing body, the blended body, and the all body, right? So that difference, when you're doing vehicle layout, and since you were locked in on one, you overlooked to understand what is the impact of the other cross section, right? And since I didn't synchronize the three teams together, what we are right now missing is really to learn what's the advantage of the wing body vehicle, what's the disadvantage of the wing body, what's the advantage or disadvantage of the all body, and the blended body is sort of this thing in between, right? So let me kick this off. Chief engineer synthesis folks, just start to ask some good challenging questions. How trustworthy the sizing is looking to you?
I did have one question for the other team. It was for reach suborbitals. From my research that I did, it was related to the tau values mainly. You said you had a tau range of, I believe it was 0.2 to 0.4, and anything higher than usually that I saw 0.3, it didn't really, I didn't find very many vehicles, if any at all, that had that kind of value. So what was your justification for going that high on your tau values for scaling?
Our tau value ranges were from 0.1 to 0.4, and we were considering the geometries laid out in not spacecraft propulsion. I'm sorry.
It's future spacecraft propulsion. That's the book.
Thank you.
So that was based on that.
That is Dr. Chudoba's textbook.
What book is that?
I'll take over for SK if he wants, because I talked on that side. So the 0.4 was we didn't expect to get a vehicle up there. We just wanted to examine out to that. We were really expecting a vehicle closer to at the far end 0.25, maybe 0.3, but our tau value ended up being 0.16, which is close to what we see for real vehicles. So it was more just let's see what's out there. And if you go back and look at our solution space, none of those vehicles are able to even take off, which is
I don't know if you saw the ice cream cone there.
Yeah, it's part of the reason we went through so many design iterations, all 5 of them.
Right. I was just wondering because when I was doing my solution spaces, I never saw a tau value getting anything above 0.25 that could make it. So I was just curious.
By the way, do you guys realize the conversation you right now have? I mean, I'm just seeing the ping pong where you agree, and because we have been sort of utilizing a common methodology. Do you know that most space launch and hypersonic vehicle designers nowadays in companies never have that discussion because they never use these types of tools? They never use something like this. They rather fall onto a point design. They do some statistics, but they never even consider tau. That is a very I wouldn't say a novel thing, but it's something what we are exclusively doing here. And by the way, it comes from McDonnell Douglas, from the secret Copper Canyon type of study, the black study, which was the precursor to NASP. And then McDonnell Douglas became basically the lead configurer for the NASP vehicle overall. So basically this TOW methodology, by the way, TOW was not invented by surely McDonnell Douglas. Cushman is using it. In case you have seen it in Cushman's book, it is discussed, and it's attributed to different gentlemen overall. But it's the mentality of holistically seeing the solution space, right? The mentality of seeing the big picture, identifying what opportunities you have, what alternatives are out there, be able to discuss the merits, and then eventually picking a baseline design. This is such a, to you now, it may feel very common sense. That's how you have to operate. But this is really usually not at all happening in the very industry. By the way, that was the reason why I left the very industries I've been attending, because most of these companies are very quickly falling onto a point design where they have experience. Remember, companies like Boeing usually go then for the wing body vehicle because they have experience. That's why the X-37B is a wing body. The space shuttle owned by Boeing nowadays is a wing body, right? There's a lot of legacy, and then there's a lot of bias in there, right? Engineers are familiar with it, and then you again slip into this. And you may have seen in the press a lot of hypersonic demonstrator vehicles, wing body vehicles, because you can calculate them with Raymer. So what you are doing here, and that very discussion you already started, it's such a novel thing, because right now you're branching out into very different terrain. What is the power of the old body? What may be the advantage of the wing body? And by the way, it's always this internal volume versus wetted surface area, right? That game, and so sorry, I didn't really mean to interrupt the discussion which started to evolve over here, but I really wanted to make that point of how novel that is, what you have been doing there. Because most companies who are a startup, do you think they're building an MDA? Do you think they're standing there, the chief engineers asking now his teams to build IDAs and MDAs? That is how a team should derive the tools. But mostly they're all in a rush, and they think they're in a rush, and somebody has a picture, and that's what we're scaling up. And then they are making the mistake of photographic scaling and not TOW scaling necessarily, right? And all the problems creep in. And then currently we see a lot of companies or startups popping up, which go back in the finesse of how they deal and design hypersonic vehicles, which is 50 years back how the designers of the X-15 started to do that. By the way, since this is just more or less around the corner, when they designed NASP, the National Aerospace Plane, you may not know, but the community at the time thought that you can fly with an air breather to orbital velocity up to Mach 25, right? So maybe nowadays that has been reduced to maybe Mach 8 with an air breather, right? So we had this rocket-based combined cycle question before. And remember, yes, the answer you guys were giving earlier, the notion that we reduced it to a rocket engine was, it's near term. We wanted to find out how can we compete with what's right now going on with something which is more, even more simple overall. So again, chief engineer, synthesis people, solution space. What is your perception? Did your solution space confirm that yes, there's indeed a lighter weight solution to the current Blue Origin Virgin Galactic system, which is staging, I think it was the first team you made a mistake in, that Blue Origin is a single staged orbit system. It's not, it is staging, right? It has a capsule.
They do advertise it as a single stage, which is why we were saying that.
Yeah, but do you think it's single stage?
Oh, no, not at all. It's definitely two stage.
Yeah.
Somebody needs to call marketing.
Yeah. By the way, Team Reach, surely a very nice pitch as salesman, presenting that with a nice salesman tone in between. Right?
We had to
Go ahead.
We had to include you and Ian as pilots and co-pilots after a while. It was
I
too
wanted
tempting
to
to
ask
not
who's in the cockpit exactly.
So in the cockpit, so we had two passengers, two crew and two crew and 6 passengers, and we were deciding on how we should render it, and the pilot is you, Dr. Chudoba, and the co-pilot is Ian Maynard, and.
Dang it! So we are the guinea pigs. So we are going on the first test flight. That's what I'm hearing.
I don't know if you noticed in the animation, but there's actually, it fades to black right in the middle of when it's going through the cabin configuration, and then it cuts back. The reason for that is because we weren't sure if we should show, but we also had a third little placard on the back that said "Reserved for Grandma," and we weren't sure if we should show that during the presentation, but it's there. So Grandma's in the passenger.
Is welcome. Grandma is welcome.
If you want the director's cut, I'll be happy to provide you.
Oh yeah, I've got it.
So unfortunately, my grandma just passed away a few months ago with the age of 105. So she couldn't quite see that, unfortunately. But I do appreciate the grandma plaque. What a cute idea. All right. So let us turn back to synthesis. Anybody was spotting something iffy on the other team's synthesis presentation where you like to poke a little bit? Now the gloves are off, ladies and gentlemen.
Well, okay, there was one question I had for, I believe it was Helios. You had a solution space that had a converged planetform area that went above 2,000 meters squared. What values did you use to get those? Because those are really high.
Yes, so basically I just took our synthesis results and I increased it by payload, and I verified it with the total volume of the Singer 2 and the tau value.
Okay, so that one was like you put in the 220 passengers or however many the Sanger 2 held and then scaled it up that way?
Yeah, I mean, I just increased the payload weight.
Okay, all right. I was just curious because that was huge.
Yeah, here's some chat going on in the background, and now I have been in the German Air Force. Actually, I was in the German Air Force. I'm not sure whether you know that. I actually was in the German Air Force. Now you're looking at me, he must be that old, right? No, I was 1 year in the German Air Force, and I was Pershing 1B operator. I would have been part of the team to shoot the Pershing 1B with the nuclear warhead on. And although the Germans, we were not allowed to have the nuclear warhead, the Americans in Germany, they were maintaining these in order to do this. So anyhow, so some laughing is going on in the chat room down there. Overall. Okay, let me ask you a question for all 3 teams. Is there a number where all 3 teams can pitch in? What's the total weight of the propellant, the combined oxidizer and fuel? Do you have a total weight number? So we can compare that. Because we all have the common, we want to reach that altitude and the rest is glide back. Whatever, wing body, all body, whatever, right? Is there a total number you guys can share?
We do have a total number, and I believe Richard has a detailed breakdown of that number since he's base.
Combined, it's 9,248 kilograms for the RP1 and the oxidizer.
9,000 kilograms.
Yep.
You had separate figures though, correct, for like the excess fuel for plumbing and RCS fuel.
That was separate. I don't have that breakdown in front of me, but that's the fuel that we actually burned with, and there's another 3%, I believe, is what I kept in for plumbing weight.
Okay, here we have the offer, 9,000 kilograms roughly. Albatross, you have anything in the sleeve?
Yes, ours, I believe, was, according to our weights person, 7,542 kilograms combined and 633 for the RCS weight.
Okay, so you're a little bit lower. What about Helios?
So our propellant weight is in the range of like 10 to 11,000, and we verified that with our trajectory and our propulsion people.
Yeah. So any ideas? Can this be attributed to not the cross section, I guess, choice, wing body, all body, that we are basically having quite some percentage difference?
Yes. So we were thinking about that because what we were expecting is that all body will have to burn more fuel to go faster and get off the ground. That's what we were considering, and I believe if you compare our numbers to Albatross, who had a wing body, they have different numbers than ours. So.
Good. So I think we addressed this in some previous meeting earlier. So it looks like all three teams are underbidding Virgin Galactic in max takeoff weight.
In max takeoff weight for our takeoff gross weight was around 22,000, and Spaceship 2 was 10,000.
He means the combined White Knight.
Okay.
It's always the combined, yeah.
Okay. I'm sorry.
Hey Ben, where did you do the texting? I mean, were you a steward before in your life, in a different life?
Did I do with the
belts?
Oh.
That's quite an interesting pitch. Ben, question for you. So you did build quite an impressive sim there, right? I think it was not just the great way of how you guys choose to present it. Remember that it has been entirely the freedom you have chosen. And it truly has been an interesting mix of having that side, and at the same time you were switching back to the technical notion. Then you were loosening it up again with, and you guys have some great salesmen and presentation in between. I think that is, I think we all agree with that. But Ben, a question for you. To what degree did you utilize the sim to cross-check or to feed information of your disciplinary team members into the sim? How was the sim possibly utilized by refining or checking or further checking the design feasibility overall? Would you mind explaining?
Not at all. So the presentation we saw today, the videos we saw today, that was based on a modified aerodynamic model of the HL20 that I was able to get my hands on. And in that, there was, I modeled the propulsion system with the Merlin 1D, regardless of what engine we were doing, whether it was RS25, RL10, Merlin 1D, the different engines we went through, and I built the propulsion system to basically simulate the mass flow rate, emptying of the tanks, based on the initial design volume of fuel oxidizer, as well as we got to this week in the last day implementing the aerodynamic model of the aspiration. However, I didn't quite have enough time by today to get the aero model fully implemented. I was still bringing in the aero teams, multi-dimensional arrays of lift drag based on Mach, altitude, alpha, beta, as well as all the control effector data that they ran. So I'm actually still implementing those matrices in for lookup tables to run. The little bit I have implemented actually shows I was able to get lift and drag only in so far, and that was showing, this is with the current aero data for our current model, and it actually was showing based on throttling with the Merlin 1D, I could reach about 80 kilometers. And perhaps if we added an extra 1,000 or 1,500 kilograms of fuel, since we have the space internally, we would that might get us up to the 100-kilometer. With that reduced, simplified HL20 model, we were hitting 100 plus or minus 5 most runs. But
did you guys utilize any? Did you guys utilize any X33 data? Because you have similarity with the X33 VentureStar.
Not explicitly with the simulation, but definitely modeled with the geometry. Took cues from the X33, as well as when we built our for the horizontal vertical tails and control effector sizing, the dihedral. Kind of based it on some of those common, more popular all-body aircraft.
Yes, good. Remember, we are doing conceptual design, and usually the conceptual design team comes up with an airplane, and usually the high has been there's a rendering of an airplane which goes into popular science. Then we may have even a 3D print of that, right, which is another level of presentation. What you have been doing is where you have not just an animation of the VSP model rotating and fluttering around. It's a sim, and here we are in the interesting world where in a good conceptual design system, that's what we are sort of striving for here in the AVD lab, where you have a parametric flight sim, engineering flight sim, which can be utilized for a range of activities throughout, right? So you basically have touched that additional level, because now you could basically send it through a pre-prescribed flight test sequence, right? Because remember, you're only sizing an airplane for specific points in the flight envelope. You're checking the elevator, elevon for the takeoff rotation. But now having an airplane, now you could send it through a far more comprehensive flight test program, the simulation, right? And you could run this, and you could check the vehicle, and you could identify where the knowledge gaps sit. Before you even claim that you have a mature vehicle, you could further check and try to harden your early conceptual design. So by the way, I'm here in the AVD lab. Ian is sitting across, and I don't want to at all miss to thank Ian for his diligent support throughout the entire semester, because he has been the go-to person for many of you. He's a superstar in the AVD lab overall. And I'd like to give Ian possibly the final word on asking you some tough questions as the TA in the class. Ian, it's up to you.
Could we first give him a round of applause for all of his assistance and help this semester?
Ian, any comment from you?
Hey, well, thank you first of all, and I did have a few questions. I mean, when y'all were talking about the cabin pressurization, I was curious if anyone can.
By the way, my list of questions is long. Now you guys have been doing awesome. All right, Ian, sorry.
Yeah, something else I was thinking about is sometimes aircraft have to constrain their climb rate or descent rate based on cabin pressurization, like how quickly or how slowly it's pressurizing or depressurizing. I was curious if anyone looked into that or thought about that.
Oh, Ian, you're referring to whether you have a pressurization system, and since the ascent is fast.
Yes, whether so basically
that's an interesting thought. Yeah, because a normal, let's say, a Learjet is climbing much slower, right? So typical pressurization systems, the AC units, etc., are surely they're not the standard systems for these types of airplanes, where you have to make sure that your passengers are not passing out due to lack of oxygen during the ascent. Because what do you do when you are missing the announcement, fasten your seatbelts or unbuckle because you can float and you pass out, right? And we're finding out we missed that critical discipline to make sure that we are pressurizing fast enough and what energy and volume that HC unit needs as a system in the airplane, that the passengers are not sleeping when their coasting is happening. Good point. Anybody thought about that?
So I'll admit we did not think about it, but that was because our flight path angle was only 60 degrees, so we assumed that it would be most systems would be fast enough to keep up with it. So that was our kind of assumption for that, even though it wasn't stated.
So I'll go ahead and add on to that though. Even though it wasn't considered within the analysis, it was considered for safety, but the main concerns were going to be that nobody passed out, but just to maintain pressurization throughout the entire flight. That also included having a combination of both oxygen and necessary gases for everyone to stay alive, basically.
So how long do you float? I mean, what is the coasting? How long is that parabolic arc? How many minutes, how many seconds are this where you would consider this is the moment the passengers most will cherish? Anybody? Three numbers?
Henry had a really good estimate of that number, and Henry, I'd love to handle this one.
Yes, so the overall weightlessness time was about 4 minutes. It was calculated from the main energy cutoff point to apogee. It was about 110 seconds, which is a little bit like 10 more seconds than it takes for Spaceship 2. So overall, since because of the parabolic behaviors, it's going to be 4 minutes, rounded.
Good. The other two teams confirm this?
Yes,
Helios, oh, sorry.
Good.
For Helios, we calculated it to be a little over 3 minutes, about 3 minutes and 15 seconds, and that was after main engine cut off at 55 kilometers. And then we started seeing the load pick up at around 65 kilometers during reentry.
Awesome. So looks like we could now go on forever in talking about these aspects, right? But every semester has to come to an end to give you now pristine time to focus on the final other deliverable, which is the report. So all three teams, well done. Very entertaining presentation. I enjoyed all three of them. That's the beauty of diversity, that you sort of have not been sharing some of the ideas. Every presentation had nuggets, golds, sort of hidden and explicit. You had good ideas. That's sort of why that is really enriching to get exposed like this. Overall, final question from my end. Is that single stage to space tourism altitude the next step? Is there a showstopper? Is there something we have overlooked? Is that a simpler system? Is that more an airplane type system as airplane passengers are used to, which could be adopted in a follow-on third company, which might break into that marketplace?
So I was thinking about this, and based on our calculations and the number, the data that we found, I believe that if we want to have a single stage, we would have to make it last longer, because the thing that I realized is from our calculations is that a single stage, since the fuel isn't, we don't have that much fuel, we burn through it pretty quickly, and the overall flight time goes down. So that would be a marketing point that most people would look over, because most people would be thinking about other spacecrafts like Virgin Galactic, because they have a longer flight time. They're spending that 250,000 for a longer amount of time in the air. So my analysis was that if we could get a longer mission time we could get a better sales pitch, and we could get that investment going, because people won't pay that much money unless they get to enjoy it for a certain amount of time. That's what I was thinking.
Yeah, that would be now an interesting analysis between Virgin Galactic, have a sort of decision table. I mean, I'm just giving you maybe ideas for your final report, right? Where you go for a pros cons type table, where you're considering that surely Virgin Galactic with a jet powered carrier system surely can cruise out 100 miles and then possibly release overall, whereby your rocket powered ship is more or less bound to the takeoff fields that you're limited in cruise. Or if you would have a longer cruise leg to consider, right, that would basically mean you need to design a bigger vehicle with more propellant, right? So that's sort of maybe surely a limitation of the rocket powered single stage to orbit system, that you have a shorter fuse overall, and of course you want to make sure that your flight corridor where this is happening, the column where you have to clear the airspace, is sort of in connection with the spaceport. So it's a different philosophy which is underlying, right? So you have a shorter fuse overall. Is there any other philosophy anybody has to share? All right, good. Ladies and gentlemen, again, congratulations to a final presentation. Entertaining, you had a lot to present. Your presentation material has been involved, thought through. You have seen now the other teams. You surely have gained ideas of how you could have done it, where the strengths and the weaknesses are. So I do suggest utilize the remaining days you have, because remember the final report is next to the VIP presentation where you create attention with, right? What is happening is, when the presentation is appealing, people have an interest now reading the report where the truth is comprehensively documented, right? The presentation is not documenting everything. It's basically a summary section to grandma, to the CEO, to the various audiences we have been assuming. So focus on the report, and remember, 2 semesters ago you had very little idea what is happening. Now you can very much apply at some of those companies who are hiring like crazy in this country, doing the type of work, from SpaceX to Blue Origin to some of these. So I think we have the other opportunity might be that some of you might consider to pull this at the end, maybe into a research publication we are thinking about. So all of these are things maybe we are dealing about, because make sure that you as well documenting in your individual report, especially at chief engineer synthesis level, how many studies have been there before who did this comparison of the single stage versus the 2-stage vertical and horizontal type of, because right now these are pioneering, this is a pioneering era we are experiencing. So it's very exciting, especially when we are in contact still in 30 years and we are realizing how space tourism is locking themselves in. You were one of the first who considered quite an attractive alternative. So overall, wonderful presentations, very entertaining, technical, savvy, well sold. Focus on your final report, and thank you very much for that presentation.
I had one quick snippet to show you. Actually, I was considering putting this in our presentation, but I didn't know if we had enough time. Let me share my screen. So thanks to Ben, we got the simulation working, and if anyone wants to fly our aircraft, they can actually do that with the joystick. So we can maybe include a Veed Sub-Orbitals texture pack for future simulations.
Yes, so I mentioned this. I've been working here in the lab. We are working on, of course, of course, a capable synthesis system for space launch, for hypersonic vehicle design, space tourism. And years ago, we have been working with a researcher who has been building a simulator of that sort. And one of our first PhDs here at UTA, Amit Oza, you may have seen his PhD thesis. He started working on this. So here we have a savvy, surely grad topic, which is pending and open. So in case somebody has an interest, because remember Neil Armstrong's X-15, the one Neil Armstrong was flying eventually, was as well flown with a stick and some instruments in one of the first analog flight sims, right, in order to explore. Remember, whatever we are all doing here, whether we are just calculating a stability control equation, whether stability is there, or whether some of that additionally gets explored in a sim like Ben has been doing this to some degree, right? The goal is to reduce the risk. The goal is to identify, is this a good design? We are doing forecasting, we're looking into the future. And you guys have produced a very interesting snapshot in space tourism overall. And thank you so much.
Can we
have
take
a great end of the semester?
Class,
yes.
Can we take a class picture with everybody's cameras on?
Yes.
If everybody wouldn't mind.
We can get the together mode or whatever it's called.
Right.
Do we have to press together mode, or like does somebody else do it?
You have to do it, Run.
You have to do it.
Yeah.
Okay.
Well, each person, I think, changes the view into
I have together mode on. Unbelievable. I didn't know that it's there. All right. Anybody still coming, jumping in? All right.
Is this everybody?
The tall gentleman to the back, please. Fasten your seatbelts. All right. Looks like we are complete. Okay, got it. Thank you so much, everybody.
Yes, thank you.
Thank you, Professor.
Thanks, everybody.
Professor. It has been a pleasure.
It's been a wonderful semester.
Bye, everybody.
Thank you.
Get some sleep.
Oh, yes, absolutely.
First on my list.
Yeah.
He knows
right,
so
see
well.
you guys.
All right, be good, everybody.
This is recorded.